Welcome to this calm documentary about the Cambrian Explosion and how life in Earth's oceans began to change. If you enjoy relaxing science stories like this, please consider giving the video a like, subscribing to the channel, and sharing it with someone who might also fall asleep to documentaries. Thank you so much for spending your time here today. I would love to know, what time of day do you usually listen to this kind of video? And where are you watching or listening from? Feel free to let me know in the comments. Now, let us begin. At the beginning of the Cambrian interval, Earth turns beneath a cool, thin atmosphere, and the solid planet presents an arrangement of land and water that persists for many millions of years. Most large land masses lie in the southern hemisphere. A great composite continent, later known as Gondwana, spans mid and high southern latitudes, while other continental blocks, such as Laurentia Baltica and Siberia, sit closer to the equator as more isolated plates. None of these continents carry forests or rooted plants. Their surfaces are bare or only lightly coated by simple microbial films, so the color and texture of the land come mainly from rock-loose sediment and thin soils, rather than from vegetation. Tectonic plates move slowly on human timescales, but steadily on geological ones, and continental outlines shift only over tens of millions of years. Long mountain belts mark the scars of earlier collisions, while rifted margins record episodes when continents pulled apart. Erosion works on these highlands, breaking rock into fragments and dissolving minerals. Rivers carry this material toward the lowlands and coastal zones, feeding systems of deltas and shallow marine plains where sediments accumulate in thick, laterally extensive layers. Along many continental margins, the land is partly flooded by broad, shallow seas. These epicontinental seas spread inland over low-lying crust and connect with the open ocean at continental edges. Global sea level in the early Cambrian is generally high. Several factors contribute to this: a relatively warm climate with limited permanent ice on land, the presence of young, buoyant oceanic crust at spreading ridges, and long-term cycles of crustal loading and unloading. When new oceanic crust forms along mid-ocean ridges, it is warm and elevated, displacing seawater outward and onto the continents. Over time, as the crust cools and subsides, sea level can fall. But during intervals of extensive ridge activity, background sea level stays raised. The difference in height between deep ocean basins and flooded shelves shapes how water can move where wave energy is focused and where mud, sands, and carbonate settle. In the interiors of the continents, the absence of plants and soils with deep roots changes how landscapes behave. Rainfall runs off more easily from bare rock and thin regolith, and winds can move fine dust across wide distances without being trapped by vegetation. Some regions are arid with large dune fields and ephemeral streams, while others experience more regular rainfall that supports the formation of thicker weathered layers and networks of rivers. Lakes and inland seas may form in low-lying areas, but without land plants, they lack the type of organic, rich shorelines familiar from later periods. On long time scales, these continental conditions influence the rate at which elements such as calcium, magnesium, phosphorus, and silica are delivered to the oceans. The climate backdrop of the early Cambrian follows the long recovery from more extreme ice ages in the late Precambrian. Geological evidence from older rocks shows that large ice sheets once reached low latitudes, but by early Cambrian time, these ice bodies have retreated or vanished, leaving behind striated bedrock glacial tillites and outwash sediments. The planet is no longer in a near-global glaciated state. Instead, it sits in an interval with moderate to warm surface temperatures. Broad zones experience temperate to subtropical conditions, particularly around low latitudes where many continental blocks reside. Seasonal cycles are controlled by the tilt of Earth's axis and its orbit around the Sun as they are today. With less extensive polar ice than in some later geological periods, the contrast between equatorial and polar temperatures is present but not extreme. Storm systems move across the oceans and flooded shelves, bringing changing patterns of wind and rain to the continents. Over very long times, chemical weathering of silicate rocks draws down carbon dioxide, while volcanic outgassing and metamorphic reactions return it to the atmosphere, forming a slow feedback that helps regulate climate. Heat flow from Earth's interior is higher than at present because radioactive elements that release heat have had less time to decay. This elevated heat flow contributes to somewhat more rapid production of oceanic crust and influences the shapes of ocean basins. The deep parts of the ocean lie far from the continents, where old cold crust has subsided, while shallower regions occur nearer the margins and beneath the epicontinental seas. These differences in depth affect how water masses can circulate and how sensitive sea level is to changes in the volume and temperature of seawater. The rotation of the planet and the pull of the moon generate tides that raise and lower sea surfaces along coasts and across shallow platforms. In the early Cambrian, the length of day is slightly shorter than 24 hours because tidal friction has not yet slowed Earth's spin to its modern value, and the moon orbits somewhat closer than it does today. These physical details alter the strength and timing of tides, which in turn influence coastal erosion, sediment transport, and the stirring of shallow marine waters. On the continents, repeated cycles of uplift and erosion linked to plate tectonics create a patchwork of terrains at different elevations. Some regions host active volcanic arcs, where subduction transports water and sediments into the mantle and drives the ascent of magmas. Volcanoes in these zones build mountain chains and release gases and ash to the atmosphere while also supplying fresh volcanic rock that weathers rapidly. Other regions are tectonically quieter, with broad, stable cratons that have persisted for billions of years and now serve as basement for thick successions of sedimentary rocks. Together, these varied tectonic settings control the pattern of river systems, the size of drainage basins, and the character of the sediment and dissolved material delivered to the sea. From a planetary point of view, early Cambrian Earth can be described as a water-dominated world, with continents clustered mainly in one hemisphere high, but fluctuating sea levels that flood large portions of the continental margins, and a climate that is warm enough to keep most surface water liquid, but not so warm as to eliminate all high-latitude ice. The sun is slightly less luminous than it will be in later eras, yet levels of greenhouse gases in the atmosphere maintain surface temperatures compatible with extensive oceans and shallow seas. Over spans of millions of years, slow interactions among tectonics, erosion, and climate adjust the height of continents relative to sea level and the shapes of ocean basins. In combination, the arrangement of continents and oceans, the long-term climate background, and the typical tendencies of sea level define the broad outer boundary conditions of the Cambrian world. Within these conditions, later changes in atmosphere, oceans, sea floors, and living communities will unfold. But in this wide view, the focus remains on the solid planet, its moving plates, and the distribution of land and water that forms the physical frame for everything that follows. In the early Cambrian interval, the air above the seas forms a thin, mobile layer that both responds to the solid earth below and shapes conditions in the waters beneath. The atmosphere contains nitrogen as its most abundant gas as in later times, but the amounts of oxygen and greenhouse gases differ from modern values. Geological and geochemical evidence suggests that free oxygen has already risen from the very low levels of the distant past to a substantial fraction of present atmospheric levels, yet it still probably falls short of the roughly 1/5 of the atmosphere seen in later eras. Carbon dioxide concentrations are higher than in recent centuries, maintained by volcanic degassing at spreading ridges and island arcs, by metamorphic reactions in the crust, and by the absence of extensive land plants that would otherwise draw down carbon through rapid weathering and burial. Water vapor. Another greenhouse gas moves constantly through the atmosphere as it evaporates from the ocean's surface and condenses in clouds. Small amounts of other gases, such as methane and sulfur-bearing species, are present especially near active volcanic regions, but they form only minor components of the overall mixture. Together, these gases control how much solar energy the planet retains and how heat is moved between the equator and the poles. The chemical state of the atmosphere affects the penetration of high-energy radiation. By the early Cambrian interval, a protective ozone layer has formed in the upper atmosphere as molecular oxygen is split by ultraviolet light and recombines into ozone. This layer absorbs much of the most damaging ultraviolet radiation before it can reach the surface. Even so, the spectral quality of sunlight at sea level is not identical to that of later times. Slightly lower oxygen levels and higher greenhouse gas concentrations influence scattering and absorption in subtle ways, and the absence of abundant land vegetation means that dust and small mineral particles can be more easily lifted from dry continental surfaces. Winds carry this fine material over the oceans, where it contributes to atmospheric haze and provides nuclei on which cloud droplets can form. In some regions, particularly downwind of arid continental interiors, the sky may contain a persistent background of dust, which softens the directness of sunlight and shifts the balance between direct and diffuse light, reaching the sea surface. Atmospheric circulation in the early Cambrian interval follows the same basic physical rules as in later ages. Differential heating between equatorial and polar regions generates broad bands of rising and sinking air, while the rotation of the planet deflects moving air masses and produces prevailing wind belts. Over low latitudes, rising warm air produces zones of frequent cloud formation and rainfall. At higher latitudes, air descends and dries, favoring more stable conditions and, in some places, aridity. Embedded within these large-scale patterns are storm systems where pressure gradients drive stronger winds and concentrated precipitation. As these systems move over the oceans, they roughen the sea surface, deepen the mixed layer of surface water, and influence the delivery of gases to and from the ocean. Whitecaps and spray increase the contact area between air and water, enhancing the exchange of oxygen, carbon dioxide, and other gases. During calm intervals, the air above the ocean is stably stratified with gentle winds that allow the formation of thin marine boundary layers in which temperature, humidity, and gas concentrations adjust gradually. Light from the sun arrives at the top of the atmosphere with an intensity that is slightly lower than in later geological periods because the sun itself is still slowly brightening over its main sequence lifetime. The difference is modest, and the combination of elevated greenhouse gases and atmospheric circulation maintains surface temperatures that keep most ocean water liquid. As sunlight passes through the atmosphere, it is scattered by gas molecules, dust, and cloud droplets. Shorter wavelengths are scattered more strongly, giving a bluish cast to the diffuse sky, while longer wavelengths travel more directly toward the surface. The balance between direct and diffuse light depends on cloud cover and aerosol loading. Under clear skies over mid-ocean regions, a large fraction of incoming solar energy reaches the sea surface as direct beams. Under hazier or cloudier conditions, the light becomes more diffuse, arriving from many angles and penetrating the water column differently. At the interface between air and sea, the surface state of the water further modulates how light enters the ocean. When winds are low and the sea surface is smooth, a larger proportion of incoming light passes straight into the water with only a small fraction reflected back toward the sky. When winds increase and waves form, the rough surface scatters light in many directions, slightly increasing reflection, but also allowing light to enter the water at a wide range of angles. Foam and bubbles from breaking waves can brighten the surface, but may temporarily reduce penetration into the water just below. The color of the ocean itself depends on the interaction between incoming light and the substances dissolved or suspended in the water. Pure water absorbs red and infrared wavelengths more strongly, allowing blue and green light to penetrate to greater depths. However, natural seawater contains dissolved organic molecules, fine mineral particles delivered by rivers and dust, and living microscopic organisms, such as cyanobacteria and algae. Each of these materials has its own pattern of absorption and scattering, so the spectrum of light changes steadily with depth. Near river mouths and along turbidity plumes from eroding coasts, the upper water may appear green or brownish, and light may be attenuated within a few tens of meters. Far from land in clearer oceanic regions, blue light can penetrate to greater depths, setting the thickness of the sunlit layer where photosynthesis is possible. Clouds play a central role in shaping the daily and seasonal rhythm of light over Cambrian seas. Low, thick clouds reflect a large fraction of incoming sunlight back to space, cooling the surface beneath and dimming the waters below. High, thin clouds allow more visible light to pass through, but trap outgoing infrared radiation, influencing the heat budget differently. The distribution of cloud types follows patterns of atmospheric circulation, topography, and sea surface temperature. Over warm, shallow epicontinental seas that cover parts of the continents, evaporation can be strong, feeding moisture into the lower atmosphere and sustaining scattered cumulus clouds and occasional storms. Over cooler waters at higher latitudes, stratiform cloud decks may form more frequently, producing extended periods of diffuse low-contrast light over the ocean surface. These variations in cloudiness cause the amount of light available at the sea surface to fluctuate on timescales from hours to years. The exchange of gases between atmosphere and ocean is continuous. Carbon dioxide dissolves into surface waters where it reacts with water molecules to form a set of dissolved inorganic carbon species. The balance among these forms depends on temperature alkalinity and the total amount of dissolved carbon, and it sets the acidity of seawater. In the early Cambrian interval, higher atmospheric carbon dioxide tends to increase the amount of dissolved carbon in the ocean, but mineral weathering on land and the burial of carbonate minerals on the seafloor provide counteracting processes. Oxygen similarly crosses the air-sea boundary, dissolving into the surface ocean during windy, cool, and turbulent conditions and escaping back into the atmosphere when surface waters become oversaturated. Because the atmosphere acts as a large reservoir with long mixing times, these exchanges smooth out regional differences over long intervals while still allowing local fluctuations linked to temperature, weather, and biological activity. Dust and volcanic aerosols supplied from the continents and arcs not only affect the optical properties of the atmosphere, but also serve as carriers of nutrients. Tiny particles rich in iron, phosphorus, and trace metals fall from the air into the ocean, either directly or washed out by rain. When these particles reach the sea surface, they can slowly dissolve or be incorporated into sinking aggregates, adding small but widespread fluxes of essential elements to the upper ocean. The rate and pattern of this atmospheric deposition respond to the positions of arid regions, the frequency of volcanic eruptions, and the strength of prevailing winds. Over millions of years, changes in these factors help modulate the nutrient status of different marine regions even before considering processes inside the ocean itself. Taken together, the composition, circulation, and optical properties of the early Cambrian atmosphere define the conditions under which sunlight, heat, and chemically active gases reach the ocean's surface. The air is neither uniform nor static. It varies from place to place and through time as storm systems form and decay, as volcanic eruptions inject ash and gases, and as long-term balances among greenhouse gases shift. Yet, within this variability, the atmosphere maintains a broad, relatively stable range of temperatures and light levels across most of the globe. Overlying the flooded continental margins and open ocean basins, it acts as both a filter that shapes the spectrum and intensity of light and a reservoir that exchanges gases and particles with the sea below. This continuous interaction forms the atmospheric boundary conditions for the Cambrian oceans, setting the outer context for the structure and behavior of the water column that lies beneath the surface. Beneath the moving air and changing light, the Cambrian oceans fill a set of basins whose shapes and connections guide the flow of water and the distribution of conditions within the water column. The solid floor of the ocean is built of crust formed along mid-ocean ridges where mantle material rises, melts, and cools. Newly created crust near these ridges is warm and buoyant, standing higher than older crust that has moved away and cooled. As a result, the ocean basins are not simple flat depressions, but broad, gently sloping surfaces that deepen from ridge crests toward distant trenches and continental margins. The average depth of the deep ocean basins is several kilometers, but the exact values vary with crustal age, local tectonic loading, and sediment fill. In the early Cambrian interval, the rate at which new crust is produced is somewhat higher than in many later times, because the internal heat of the planet is still greater. This higher production rate tends to keep ridge systems more elevated and contributes to the high global sea levels that flood many continental margins. The outlines of the basins are further shaped by subduction zones, where old oceanic crust bends and sinks back into the mantle, creating deep trenches that mark the edges of plates. Island arcs, with their chains of volcanoes, rise above some of these subduction zones and form partial barriers between adjacent basins and marginal seas. Between ridges, arcs, and continents, the ocean is divided into a mosaic of connected but distinct regions that differ in depth, width, and degree of enclosure. These structural differences have direct consequences for how water circulates, mixes, and stratifies. On the scale of entire basins, temperature and salinity contrasts drive slow, persistent overturning of water masses. Warm, relatively fresh surface waters form in low and mid-latitudes where solar heating and rainfall dominate. Toward the poles, surface waters cool and may become saltier as sea ice forms seasonally and excludes salt. When water becomes dense enough, it tends to sink and spread along the depths, forming deep and intermediate layers that can travel great distances before rising again. The precise patterns of this overturning circulation in the early Cambrian interval are difficult to reconstruct because direct evidence is scarce and must be inferred from chemical signals in ancient rocks. However, the same basic physical principles apply. Basins that are broad and open to the global ocean can support large-scale circulation cells that connect surface and deep waters over thousands of kilometers. Basins that are more restricted by sills, land bridges, or island chains may develop more isolated water masses with limited exchange across their boundaries. In such settings, deep waters can become depleted in oxygen and enriched in dissolved metals and reduced species if they are cut off from regular ventilation. The shape of the seafloor also controls where thick deposits of sediment accumulate and where the crust remains relatively bare. Along continental margins, broad shelves and slopes receive riverborne sediments from the continents and reworked material from coastal erosion. Gravity flows carry sand and mud down submarine canyons onto deeper parts of the basin where they spread into submarine fans. In contrast, in the central parts of deep basins, far from land sedimentation rates are lower, and the seafloor may be covered mainly by fine particles that settle slowly through the water column, including the remains of planktonic microorganisms and tiny mineral grains delivered from the atmosphere. In the early Cambrian, the absence of land plants on the continents influences both the types and amounts of sediment delivered, but the fundamental pattern of thick wedge-shaped sedimentary accumulations along margins and thinner blankets in the basin centers is already established. These sediment packages, now preserved as rock, later provide a record of the changing conditions in the overlying water column, including signs of oxygenation state, nutrient supply, and biological activity. Within the water column itself, physical structure arises from the interaction of heating, cooling, evaporation, precipitation, and wind-driven mixing. In low-latitude regions, strong solar heating warms the surface layer, making it lighter than the cooler, deeper water. This density contrast can form a thermocline, which is a zone of rapid temperature change with depth that separates a warm, well-mixed surface layer from a colder, more stable, deep layer. The strength and depth of this thermocline vary with season wind stress and regional circulation patterns. In areas with persistent upwelling where winds drive surface water away from coasts or along basin boundaries, deeper, cooler, and nutrient-rich waters can rise toward the surface, weakening the stratification locally. In high-latitude regions, weaker heating and stronger cooling can allow vertical mixing to reach deeper, sometimes eroding the thermocline and connecting surface waters more directly with the interior of the ocean. In semi-enclosed basins and epicontinental seas, evaporation and freshwater input from rivers or rainfall can create additional density contrasts by altering salinity. These processes together generate a patchwork of water column structures from strongly stratified layered systems to more weakly stratified or well-mixed ones. The paths that water takes around the basins are also influenced by the Coriolis effect arising from planetary rotation. As water moves along the surface under the push of winds, it is deflected to one side, creating broad gyres in the subtropical regions of the oceans. These gyres often bring warm waters along the western sides of ocean basins and cooler waters along the eastern sides. Along continental margins, the interaction between currents, wind, and bottom topography can generate boundary currents that flow poleward or equatorward, depending on hemisphere and prevailing wind patterns. Even on continental shelves and in shallow epicontinental seas, the combination of tides, wind-driven currents, and density-driven flows produces complex circulation patterns that shape how heat, salt, oxygen, and nutrients are distributed. In straits and narrow passages between basins, strong tidal currents can enhance mixing and draw deep water into shallower regions, or export surface waters into the open ocean. During the early Cambrian interval, these circulation patterns operate in basins that differ from today's oceans in their exact configuration, but not in their fundamental physics. The arrangement of continents, island arcs, and ridges sets where major gyres and overturning cells can form, while the climate background sets the range of temperatures and salinities available to build density contrasts. Where deep waters form and where they spread along the seafloor determine which parts of the basin floors receive oxygen-rich waters and which may lie beneath more stagnant, oxygen-poor layers. In regions where deep water renewal is strong, the sediments at the bottom of the basin are bathed in oxygenated water, supporting benthic life and promoting the burial of oxidized minerals. In regions where renewal is weak or cut off by sills, deep waters can remain isolated for long periods, allowing the accumulated decay of sinking organic matter to consume dissolved oxygen and leading to more reducing conditions. These redox differences play a major role in controlling the solubility and mobility of elements such as iron, manganese, and phosphorus, which in turn feed back on nutrient availability in surface waters over long timescales. Marginal seas and interior seaways add further complexity. Where epicontinental seas flood low-lying interiors of continents, they may connect to the open ocean through one or several narrow gateways. Tidal exchange through these gateways can be vigorous, but net circulation may still be limited, especially if the seaway is shallow and sheltered from strong winds. In such cases, the water column over the flooded continental interior can stratify during warm seasons with a freshened surface layer supplied by river input overlying more saline bottom water. If mixing is insufficient to ventilate the deep layer, oxygen levels there can fall, and the sediments may record intervals of low oxygen or anoxia. Elsewhere, more open interior seas with wide connections to the ocean and higher wind energy can remain well mixed with oxygenated bottom waters and more uniform conditions with depth. The balance between these outcomes depends sensitively on basin geometry, sill depths, and the relative strengths of tidal wind and density-driven flows. Over millions of years, the architecture of the Cambrian ocean basins is not static. Plate motions gradually rearrange continents and seafloor spreading centers, opening new basins and closing old ones. As plates converge, oceanic crust can be subducted and trenches can migrate, while collision between continents can raise new mountain belts. These tectonic adjustments change the depth and width of basins, the positions of gateways, and the connectivity of epicontinental seas. Even modest shifts in sill depth or basin shape can alter circulation pathways enough to transform patterns of oxygenation and nutrient distribution in the overlying water column. Thus, while the physical laws governing fluid flow and heat transfer remain the same, the specific manifestation of circulation and stratification in the early Cambrian oceans is tightly linked to the evolving three-dimensional architecture of the basins themselves. This architecture defines the large-scale physical framework inside which finer-scale processes on shelves in the water column and at the seafloor will later influence the environments experienced by early animals and their microbial precursors. In the early Cambrian interval, much of the interaction between solid earth and ocean takes place across broad continental shelves and shallow seafloor settings that rim the continents and extend inland where epicontinental seas flood low-lying regions. These shelves form gently sloping surfaces that begin near ancient coastlines and deepen gradually toward the outer shelf and upper continental slope. Water depths over most shelf areas range from a few meters near shore to a few hundred meters near the shelf break, though exact values vary with local subsidence, sediment accumulation, and sea level. Because global sea level stands high in this interval, many continental margins host particularly wide shelves, and interior seas cover regions that were previously exposed land. These flooded surfaces create extensive areas of shallow marine habitat that are bathed in sunlight and subject to waves, tides, and currents generated by the atmosphere and the motion of the moon and earth. The shape of each shelf depends on the underlying crustal structure and the history of tectonic and sedimentary processes in that region. Along some margins, long-lived rivers have built out deltas and coastal plains, creating gentle gradients that allow shallow water to extend far from the original continental edge. In other places, tectonic uplift or faulting has produced steeper margins where the shelf is narrow and the seabed drops quickly into deep water. Ancient mountain belts that lie near some coasts supply abundant sediment, while more stable cratonic interiors feed smaller, more dispersed sediment loads. Where epicontinental seas reach far inland over low-relief surfaces, their floors can be broadly uniform with only subtle variations in depth and slope. On these shelves, the physical environment is strongly shaped by waves and storms. In fair weather, small wind-generated waves disturb only the upmost layer of the seabed near the shore, leaving deeper areas relatively undisturbed. During storms, however, larger waves with longer wavelengths can reach to tens of meters depth, or more risk suspending sand and mud and transporting them across the shelf. Over many cycles of calm and storm, this alternating disturbance produces characteristic sedimentary structures. Coarser sand tends to accumulate in higher energy zones, closer to shore, and in pathways swept by strong currents, while finer mud settles in quieter areas between storm events. In the rock record of early Cambrian shelves, these processes leave signatures in the form of cross-bedding, graded beds from storm deposits, and layers of mudstone that represent calmer intervals. At the time, these features are simply the result of constant mechanical reworking by waves, tides, and currents acting on unconsolidated sediment. Tidal forces play a major role in many Cambrian shelf settings. The gravitational interaction between Earth and the Moon produces regular rises and falls of sea level along coastlines and across shallow seas. Where the geometry of coastlines and seafloor contours focuses tidal energy, strong tidal currents can develop. These currents flow in and out of embayments through narrow straits and across broad flats, shaping sandbars, tidal channels, and shoals. On intertidal and very shallow subtidal flats, repeated exposure and flooding with each tide create conditions for alternating wetting and drying salt concentration and mechanical compaction of the surface sediment. In slightly deeper areas that remain submerged, tidal currents can winnow fine particles from the seabed, leaving behind rippled sand and forming sand waves that migrate slowly over time. In quieter parts of epicontinental seas, where tidal energy is weaker, finer-grained sediment can accumulate more continuously, creating more uniform, mud-rich seafloors. The absence of rooted land plants along early Cambrian coast influences how these shelves look and function. Without vegetation to stabilize shorelines, riverbanks and delta plains erosion during floods can be more direct, and channels may shift frequently across their floodplains. Sediment delivered to the coastline is not trapped by coastal marshes or mangrove forests, which do not yet exist. Instead, sand, silt, and clay enter the coastal ocean in relatively open plumes. Fresh water from rivers mixes with seawater over tens to hundreds of kilometers, forming gradients in salinity and density that influence local circulation and stratification. In the surface layers, near river mouth, suspended sediment can reduce light penetration and create turbid zones, where conditions differ from the clearer waters offshore. As the plumes disperse and sediments settle, the material contributes to the growth of deltas, progradation of coastlines in some regions, and the infilling of small basins within epicontinental seas. Temperature conditions on shelves also vary with latitude, ocean circulation, and seasonal cycles. Low-latitude shelves that lie under warm, sunlit skies and receive steady trade winds tend to host relatively warm surface waters for much of the year. These conditions favor high rates of evaporation, which can increase surface salinity, particularly in semi-enclosed interior seas. In some of these warm, shallow regions, if the chemistry is favorable, carbonate minerals precipitate directly from seawater or are produced by microbial activity coating grains and forming lime-rich muds and sands. Over long periods, such processes can build thick carbonate platforms that stand as broad, flat-topped regions within the shallow ocean. On higher latitude, shelves' cooler conditions and weaker sunlight reduce evaporation and limit the extent of carbonate precipitation. Here, siliciclastic sediments derived from the erosion of continental rocks dominate, forming layers of sandstone, siltstone, and mudstone on the shelf floor. The interplay between temperature, salinity, and local circulation also influences how well mixed the water column is over the shelf. In many regions, wind stress and tides keep the shallow water relatively well mixed from surface to seabed, especially during cooler seasons when surface heating is weak. In others, particularly where river input creates a fresh surface layer, stratification can develop seasonally or persistently with a lighter upper layer overlying a denser, saltier bottom layer. When stratification is strong, oxygen and heat from the surface may not penetrate efficiently to the seabed, and bottom waters can become less oxygen-rich if the consumption of oxygen by the decay of organic matter is high. When winds or storms break down this layering oxygen, rich surface waters can again reach the seafloor. These cycles of stratification and mixing influence not only the chemical state of the bottom waters, but also the physical stability of the sediments and any structures or traces present within them. Light penetrates the water column over shelves to depths that depend on water clarity, which is controlled by suspended sediment, dissolved organic compounds, and the abundance of microscopic photosynthetic organisms. In clear, low sediment regions, sunlight can reach tens of meters below the surface, establishing a broad zone where photosynthesis is possible on the seabed or in the overlying water. In turbid near-shore zones or river-influenced areas, the depth of the well-lit zone may be reduced to only a few meters. The distribution of light with depth and distance from shore creates a gradient of conditions across the shelf, from bright wave-agitated shallows to dimmer, more tranquil outer shelf settings. In each zone, the combination of light physical disturbance and sediment character shapes which types of microbial communities and later early animals can occupy the substrate. The shallow seafloor itself is composed of a patchwork of substrates with differing grain sizes and degrees of consolidation. Coarse, sandy bottoms in high-energy zones are easily reworked and rarely allow fine particles to settle for long. Muddy bottoms in protected embayments or deeper outer shelf settings are softer and more cohesive, storing organic matter and fine mineral grains. In some warm, clear environments, carbonate sediments form the bulk of the seabed, and structures such as low mounds or shoals may develop where carbonate production and accumulation outpace physical removal. Over time, early cementation within these sediments can begin to bind grains together, forming firmer grounds that resist erosion more effectively. Relic surfaces from earlier low stands, such as hard grounds or eroded rock platforms, may also lie beneath thin veneers of younger sediment, adding further heterogeneity to the seafloor. Across this range of shelf and shallow seafloor environments, physical processes operate continuously. Waves and tides maintain a background level of motion. Storms provide intermittent but powerful disturbance, and river discharge and atmospheric deposition deliver new material from land and air. Sediments are transported, sorted, and deposited in patterns that reflect the balance among these forces. In the early Cambrian interval, these patterns create extensive, varied, shallow marine settings that are physically dynamic, yet maintain long-term structural characteristics tied to basin-shaped climate and sea level. These settings form the immediate environment in which the chemistry of seawater interacts with sediment, and in which microbial communities occupy surfaces and pore spaces. But at this stage, the focus remains on their physical form and behavior as the shallow interface between continents and the overlying ocean. In the early Cambrian interval, the waters that fill the ocean basins and spread across continental shelves carry a complex mixture of dissolved salts, gases, and nutrients that reflect long histories of rock weathering, volcanic activity, and exchanges with the seafloor. The major dissolved ions that dominate seawater, including those based on sodium chloride, magnesium, calcium sulfate, and bicarbonate, are already present in proportions that give the ocean a stable overall salinity and chemical character on long timescales. These ions derive largely from the breakdown of continental rocks by chemical weathering and from hydrothermal alteration of newly formed oceanic crust along mid-ocean ridges. Rainwater, made slightly acidic by dissolved carbon dioxide from the atmosphere, reacts with silicate and carbonate minerals on land, releasing cations and generating dissolved bicarbonate. Rivers then transport these solutes to the sea, where they mix into the surface waters and eventually spread throughout the ocean interior. At mid-ocean ridges, seawater circulates through hot, newly formed crust, exchanging elements with the rock and emerging as hydrothermal fluids enriched in metals, reduced sulfur, and other species. As these fluids mix with cold seawater minerals, precipitate, and some components are removed from solution while others are returned to the ocean in modified form. Over millions of years, these opposing fluxes between land, ocean, and crust maintain a dynamic balance that stabilizes the broad composition of seawater. Against this backdrop of major ions, smaller but crucial pools of nutrients govern the productivity of photosynthetic organisms in the Cambrian Ocean. Phosphorus, nitrogen, iron, and a suite of trace metals are required in small amounts for the growth of cyanobacteria, algae, and other primary producers. The supply of these elements depends on processes at Earth's surface and beneath the sea. Phosphorus is released during the weathering of apatite and other phosphate-bearing minerals in continental rocks, and is transported to the ocean by rivers adhered to particles or dissolved as phosphate. Nitrogen enters the ocean both as fixed forms produced by microorganisms that convert atmospheric nitrogen gas into biologically available compounds, and as dissolved inorganic nitrogen carried in runoff from land. Iron and other trace metals arrive attached to dust particles lifted from arid regions in riverborne sediments and in hydrothermal fluids that vent along ridge axes and at other sites of fluid flow through the crust. The balance between input and removal of these nutrients is sensitive to the redox state of the oceans and the burial of organic matter in sediments. Geological evidence from iron formation sulfur isotopes and trace metal patterns suggests that before and through the early Cambrian interval, oxygenation of the deep ocean is incomplete and spatially variable. Some parts of the ocean, especially those connected to sites of deep water formation and vigorous circulation, likely hold waters that are at least moderately oxygenated. Other parts, particularly restricted basins or deeper layers beneath strongly stratified regions, may remain low in oxygen or even anoxic for extended periods. In such oxygen-poor environments, reduced forms of iron and other metals can remain soluble and accumulate in the water column, and phosphorus can be released from sediments rather than being locked away. When these waters eventually mix with more oxygen-rich regions or upwell to the surface, their chemical load can influence nutrient availability and the efficiency with which the ocean stores organic carbon. The long recovery from extensive late Precambrian glaciations exerts a strong influence on early Cambrian ocean chemistry. During intervals, sometimes described as snowball, Earth states large ice sheets covered substantial fractions of the planet's surface, grinding continental rocks and storing vast volumes of frozen water. When these glaciations ended, melting ice exposed freshly abraded rock surfaces to intense weathering under greenhouse conditions maintained by high atmospheric carbon dioxide. Runoff from these landscapes carried large amounts of dissolved ions and fine particulates into the oceans, altering their chemical composition. Enhanced delivery of phosphorus and other nutrients during and after deglaciation episodes likely fueled blooms of photosynthetic microorganisms, which in turn increased the burial of organic carbon in sediments and helped raise atmospheric and oceanic oxygen levels over long timescales. By the early Cambrian interval, the most extreme pulses of this glacially driven weathering have passed, but the legacy persists in the state of the climate system, the general elevation of sea level, and the ongoing supply of weathering products from landscapes still adjusting to post-glacial conditions. The distribution of nutrients within the Cambrian oceans is governed not only by their sources, but also by the physical circulation and the biological cycling that occur within the water column. In the sunlit surface layer, photosynthetic organisms take up dissolved inorganic carbon, nitrogen, phosphorus, and trace metals to build organic matter. This process converts dissolved nutrients into particulate form and decreases nutrient concentrations in surface waters where productivity is high. As cells die or are consumed by other microorganisms, some fraction of their organic remains sinks into deeper waters as a slow rain of particles. Microbial decomposition of this material at depth releases dissolved nutrients back into the water column, often in layers below the reach of sunlight. In this way, the interior of the ocean functions as a reservoir of regenerated nutrients enriched relative to the depleted surface. The strength of this vertical gradient depends on the rate of primary production at the surface, the efficiency with which organic matter escapes recycling in the upper ocean, and the rate at which deep waters are returned to the surface by upwelling and mixing. In regions where deep, nutrient-rich waters rise to the surface productivity can be sustained at high levels. In regions where upwelling is weak and surface waters are strongly stratified, nutrients may remain trapped at depth, limiting primary production in the euphotic zone. In the early Cambrian oceans, patterns of upwelling are shaped by the positions of continents, the prevailing winds, and the structure of the basins. Along some continental margins, especially where winds blow parallel to the coast and push surface water offshore, upwelling draws deeper water upward, cooling the surface and supplying it with regenerated nutrients. Over parts of the open ocean, divergence at the boundaries of large-scale circulation cells can also bring nutrient-rich water toward the surface. Within epicontinental seas, circulation may be more sluggish, and the recycling of nutrients can be dominated by local processes, including mixing driven by tides and storms. In restricted interior basins, limited exchange with the open ocean can cause nutrients and reduced chemical species to build up in deeper layers, reinforcing low oxygen conditions. The chemical character of seawater also reflects interactions at the seafloor. On continental shelves and slopes, pore waters within sediments exchange ions with overlying bottom water. As organic matter buried in these sediments decomposes, it alters the redox state of iron, manganese, sulfur, and carbon, sometimes precipitating minerals, such as pyrite and carbonates, and sometimes releasing species, such as phosphate, back into the water column. The balance between burial and release depends on local oxygen levels, sedimentation rates, and the composition of incoming particles. In low oxygen settings, the reduction of iron and manganese oxides can liberate adsorbed phosphate, enhancing nutrient concentrations in bottom waters and potentially feeding back on productivity in overlying surface waters if mixing connects these layers. At hydrothermal vents on the deep sea floor, fluids rich in iron, manganese, and other metals enter the ocean, forming plumes that spread horizontally while cooling and diluting. Within these plumes, metal oxides precipitate and settle, but some dissolved species and nanoparticles can travel significant distances, extending the influence of vent-derived nutrients. In the early Cambrian, when deep ocean oxygenation is patchy, the chemistry of these plumes and their interaction with ambient waters may differ from later, more fully oxygenated oceans, potentially affecting the forms and availability of some trace elements important for biological function. Overlying all these processes is the slow evolution of the carbonate system, which regulates seawater acidity and the saturation state of carbonate minerals. The concentration of dissolved inorganic carbon and the ratio of its different forms determine how easily calcium carbonate can precipitate from seawater or dissolve back into it. During the early Cambrian interval, widespread deposition of carbonate sediments on some shelves and platforms indicates that parts of the ocean are supersaturated with respect to carbonate minerals, meaning that seawater can support the formation of carbonate muds and cements under appropriate conditions. At the same time, in deeper waters and in regions with high concentrations of dissolved carbon dioxide from the respiration of sinking organic matter, the saturation state is lower and carbonate dissolution can occur at or beneath the seafloor. This vertical and regional structure in carbonate chemistry influences which areas act as long-term sinks for carbon and calcium and which act as sources. It also controls how changes in the global carbon cycle, such as variations in organic carbon burial or volcanic degassing, are recorded in the isotopic composition of carbonate rocks that form during this period. In sum, the evolving chemistry of early Cambrian oceans is the result of interactions among weathering of continents, hydrothermal exchange at spreading ridges, circulation within basins, and biogeochemical transformations in the water column and sediments. Nutrients and trace metals move through this system on timescales from seasons to millions of years, supporting varying levels of primary production and influencing the distribution of oxygen in the ocean interior. These chemical patterns do not arise from any single process. Rather, they reflect the combined effects of tectonics, climate, and biological activity, operating within the physical framework of Cambrian basins and shelves. Within this outer chemical setting, later shifts in oxygen availability, energy flow, and ecological structure will take place. But at this stage, the focus rests on the composition and movement of dissolved substances that fill and connect the oceans of the early Cambrian world. In the early Cambrian interval, oxygen in the oceans does not distribute itself evenly from surface to seafloor or from one basin to another. Instead, concentrations rise and fall with depth, distance from shore, and proximity to regions where water masses form and sink. The atmosphere above already contains enough free oxygen to maintain a protective ozone layer and to support oxidative weathering on land, but the transfer of that oxygen into the deep ocean is limited by physical circulation and by the ongoing consumption of oxygen through the decay of organic matter. The result is a seascape in which some regions of the water column hold abundant dissolved oxygen, while others remain persistently low in oxygen or lack it entirely. These differences in redox state, meaning the balance between oxidized and reduced chemical forms develop because the pathways that provide oxygen and the processes that remove it do not operate with equal strength everywhere. At the sea surface, contact with the atmosphere and mixing by waves and wind keep surface waters close to equilibrium with atmospheric oxygen. Whenever winds roughen the surface, small bubbles and enhanced turbulence increase the area across which gas exchange can occur, and oxygen dissolves into the upper layer of the ocean. In regions where photosynthetic microorganisms are active, their production of oxygen during daylight can further raise concentrations locally. As a result, the upper tens of meters of the ocean in well-lit regions are generally oxygen-rich, except where very high biological activity or strong stratification causes consumption to exceed supply. Moving downward from this surface layer, the picture changes. The sinking of organic particles from the surface introduces a continuous flux of material that heterotrophic microorganisms consume as they break down complex organic compounds into simpler molecules. This respiration uses dissolved oxygen and produces carbon dioxide and other byproducts. If the downward flux of organic matter is large and mixing is limited oxygen levels in mid-depth, and deep waters can fall significantly. Where currents bring newly formed oxygenated deep water into a basin, this supply can balance the local consumption, keeping conditions at least moderately oxidizing. Where circulation is sluggish or cut off by sills and basin geometry, deep waters may not be refreshed, frequently allowing oxygen to be drawn down to very low levels over time. In the early Cambrian oceans, geological proxies indicate that such oxygen-poor or anoxic zones are widespread in some basins and depth ranges. These oxygen gradients often take the form of a transition zone known as an oxygen minimum layer. In parts of the water column, where sinking organic matter accumulates and decomposition is intense, but where there is no strong source of fresh oxygen, rich water dissolved, oxygen reaches its lowest values. Above this layer, closer to the surface, mixing and gas exchange maintain higher oxygen concentrations. Below it, in some regions, deep waters that have recently formed at high latitudes may carry more oxygen. In other regions, especially in restricted basins, where deep water formation is weak oxygen, minimum layers may merge with fully anoxic deep waters. The exact depth and thickness of these zones depend on the balance between productivity in the surface ocean sinking flux circulation and the geometry of the basin. On continental shelves and in epicontinental seas, oxygen conditions near the seafloor depend strongly on how well the water column is mixed and how much organic matter accumulates in bottom sediments. In shallow, well-mixed settings exposed to regular storms and tides, the entire water column can be ventilated frequently, ensuring that the seabed experiences oxygen-rich conditions for much of the time. In such environments, organic particles that settle to the bottom are rapidly oxidized, and redox-sensitive elements such as iron and manganese are maintained in oxidized forms. In more stratified shelves or interior seas, where a fresher surface layer overlies a denser, saltier bottom layer, seasonal or persistent density gradients can limit the downward transport of oxygen. If primary production in the surface waters is high and a significant flux of organic debris descends into the bottom layer, the oxygen stored there can be gradually depleted. Once oxygen levels fall below certain thresholds, different microbial pathways of respiration become important. Using nitrate manganese oxides, iron oxides, and sulfate as alternative oxidants. These processes produce reduced species, such as ammonium, ferrous, iron hydrogen sulfide, and methane, which accumulate in pore waters and, in more severe cases, in the overlying bottom water. The presence or absence of these reduced compounds and the minerals they form when they react later provide a record of redox conditions in Cambrian shelf sediments. Deep ocean basins show their own range of redox states. Where basins are broad and open, and where deep waters formed in cooler, higher latitude regions can flow in at depth, oxygenated conditions may extend across much of the seafloor. In these settings, sediments record features consistent with persistent exposure to oxygenated bottom water, including the preservation of certain iron oxides and the absence of minerals that form only under strongly reducing conditions. In contrast, basins that are partially isolated by sills or constricted gateways may develop deep waters with much lower oxygen content. If the renewal of deep water is slow and the input of organic matter from above remains steady, oxygen can be exhausted entirely, leading to anoxic or even euxinic conditions, the latter meaning that hydrogen sulfide is present in the water column. Under such conditions, iron released from sediments can combine with sulfide to form iron sulfide minerals, including pyrite, which accumulate in the sediment and record the reducing environment. The distribution of such deposits in early Cambrian rock successions suggests that oxygen-poor deep waters are more widespread and longer lived in some regions than in many later Phanerozoic intervals. The redox structure of the ocean also affects the cycling of key nutrients. In oxygen-rich conditions, phosphate tends to be adsorbed onto iron and manganese oxide particles and buried in sediments, while nitrogen is largely retained as nitrate. In low oxygen or anoxic settings, reduction of these metal oxides can release phosphate back into the water column, and microbial processes such as denitrification and anammox convert fixed nitrogen back into nitrogen gas, removing it from the biologically available pool. In euxinic waters where sulfide is present, some trace metals form insoluble sulfide minerals and are scavenged from the water column. These feedbacks mean that regions of the ocean that are persistently low in oxygen may become enriched in phosphorus relative to nitrogen and may carry distinct signatures in trace metal abundance. When parts of these deep, nutrient-rich but oxygen-poor waters are eventually mixed or upwelled into the sunlit zone, they can stimulate high productivity, which in turn can further enhance the formation of oxygen minimum zones downstream. In the early Cambrian interval, when the balance between global oxygen sources and sinks is still evolving and deep ocean ventilation is incomplete, such coupled physical and biogeochemical feedbacks likely maintain mosaics of oxygenated and poorly oxygenated regions across the globe. Evidence for this patchwork comes from several types of geochemical markers preserved in Cambrian sediments. Ratios of certain redox-sensitive trace metals such as molybdenum, uranium, and vanadium vary between deposits that formed under well-oxygenated versus anoxic conditions. Sulfur isotope patterns in pyrite and carbonate-associated sulfate provide information about the scale and intensity of microbial sulfate reduction and the extent to which the deep ocean resembles a globally connected reservoir or a set of partially isolated redox domains. Iron speciation, which examines how iron is partitioned among different mineral phases, can distinguish between sediments deposited under oxic ferruginous or euxinic bottom waters. The spatial distribution of these signatures indicates that while some shelf and slope environments experience well-oxygenated bottom waters, others, especially in deeper or more restricted settings, record anoxic and sometimes sulfide-rich conditions. Importantly, these redox patterns do not remain fixed throughout the Cambrian interval. Instead, they shift over millions of years, with some intervals showing expansion of oxygenated conditions and others suggesting a resurgence of low-oxygen waters. Such changes can reflect variations in organic, carbon, burial volcanic, and weathering-driven nutrient supply, and the evolving efficiency of biological pumps that transport organic matter to depth. They may also track tectonic adjustments that open or close ocean gateways, altering the paths and strengths of deep water circulation. On shorter time scales, such as thousands to hundreds of thousands of years, climatic fluctuations can modulate stratification and mixing, causing oxygen minimum zones to expand or contract. On the scale of whole basins, the geometry of continental margins, seafloor topography, and the positions of sills determine how easily dense waters can spill into neighboring regions. A deep sill allows relatively unimpeded exchange, while a shallow sill can trap dense oxygen-poor waters within a basin, especially if fresh, lighter surface waters cap the system. Over time, sedimentation gradually fills basins and raises their floors, while tectonic subsidence or uplift modifies sill depths, so the same region can experience different redox regimes at different stages of its history. Through all of these processes, the early Cambrian oceans maintain a state in which oxygen is sufficient at the global scale to support oxidative weathering on land and active carbon cycling, yet distributed in a highly uneven way across depths and regions. The planet is not in a simple, fully oxygenated state, nor is it dominated everywhere by anoxia. Instead, the oceans form a complex redox landscape with oxygen-rich surface layers, variable mid-depth oxygen minima, and deep waters that range from well-ventilated to persistently anoxic, depending on location. Continental shelves and epicontinental seas likewise span a spectrum from well-mixed oxygenated settings to stratified systems with seasonally or chronically oxygen-poor bottoms. This redox structure emerges from the interaction of atmospheric composition, ocean circulation, nutrient-driven productivity, and sea-floor exchanges, and it defines the chemical background against which the other aspects of Cambrian marine environments operate. In the early Cambrian oceans, the main source of energy that drives biological activity is sunlight that enters the upper layer of the water column and is captured by photosynthetic microorganisms. This sunlit zone, often called the euphotic layer, extends from the surface down to depths, where light becomes too weak for effective photosynthesis. Its thickness varies from place to place depending on water clarity, the presence of suspended particles, and the abundance of microscopic organisms that absorb and scatter light. In clear offshore waters, useful light can penetrate to tens of meters, whereas in turbid coastal plumes or enclosed interior seas, it may reach only a few meters. Within this band, populations of cyanobacteria and small algae convert dissolved inorganic carbon into organic matter, using light as their energy source and drawing on dissolved nutrients such as nitrogen, phosphorus, and trace metals. These primary producers form the base of the marine food and energy network. Their cells float freely as part of the plankton, drifting with currents and turbulence, while also moving slightly under their own control in response to light and nutrient gradients. The rate at which they fix carbon varies in space and time, responding to changes in light intensity, day length temperature, and nutrient supply. In regions where upwelling brings nutrient-rich deep water into the euphotic zone, primary production can be relatively high, and the water may appear greener due to dense phytoplankton populations. In more strongly stratified, nutrient-poor regions, primary production is lower, and the water remains clearer and bluer as phytoplankton biomass stays modest. Over continental shelves and in epicontinental seas, primary production is influenced by both marine and terrestrial inputs. Rivers deliver dissolved nutrients and fine particles into coastal waters, sometimes creating zones of elevated nutrient concentrations, but reduced light penetration. In such areas, phytoplankton often occupy a shallow layer close to the surface, where enough light is available, while below this shallow productive layer, the water may be dim and less favorable for photosynthesis. Tidal mixing and storms can periodically deepen the mixed layer, bringing nutrients from below, but also redistributing phytoplankton over a thicker column, which can temporarily lower their average exposure to light. In some stratified interior seas, a subsurface maximum in phytoplankton abundance may form where the combination of remaining light and higher nutrient concentrations is optimal. Across these varied settings, the total amount of organic carbon produced in the euphotic zone sets the scale for energy flow to the rest of the ecosystem. Not all organic matter produced by photosynthesis is transferred directly to larger organisms. A substantial fraction is recycled within the microbial community. Some of the organic compounds released by phytoplankton through exudation, cell lysis, or grazing become dissolved organic matter, which heterotrophic bacteria in the water column use as a substrate. These bacteria oxidize organic molecules back to carbon dioxide, consuming oxygen and regenerating nutrients in dissolved form. In turn, the bacterial populations themselves are consumed by small heterotrophic protists and very small metazoans, creating a microbial loop in which energy and matter circulate among microscopic players before any portion reaches larger consumers. This loop enhances the retention of nutrients within the euphotic zone, but also contributes to oxygen consumption in both surface and deeper layers. A portion of the organic material escapes rapid recycling near the surface and begins to sink as individual cells, fecal pellets, and aggregates of particles, often referred to as marine snow. As these particles descend, they carry with them both energy and nutrients. Microorganisms attached to or surrounding the particles continue to decompose them, releasing dissolved nutrients into the water column and producing carbon dioxide. The intensity of this remineralization determines how much organic material reaches deeper waters and eventually the seafloor. In regions with high surface production, the flux of sinking particles can be substantial, and the gradient in nutrient and oxygen concentrations with depth becomes pronounced. This export of organic matter from the surface to depth is sometimes described as a biological pump because it helps move carbon and nutrients downward against the tendency of mixing and diffusion to homogenize the water column. The efficiency of this export process in the early Cambrian oceans depends on several factors, including the sizes and compositions of planktonic organisms, the structure of the water column, and the rates of grazing and aggregation. Where plankton cells are relatively large or form sticky, exudates aggregates may form more readily, increasing the downward flux. Where grazing by small consumers is intense, more of the organic material may be repackaged into dense pellets that sink faster. The presence of mineral particles such as clay grains delivered from land or biogenic minerals formed in the water column can also promote aggregation, adding ballast that helps particles descend more rapidly through the water column. In contrast, in regions with low production and strong recycling in the surface layer, the flux of organic matter to depth is weaker, and most of the energy remains in the upper ocean. At the same time, not all biologically important energy input to the Cambrian oceans comes from sunlight. In certain environments, especially around hydrothermal vents and areas of fluid flow through the seafloor, chemical energy supports chemosynthetic microbial communities. Here, microorganisms use the energy released when reduced chemical species such as hydrogen sulfide, ferrous iron, or hydrogen are oxidized, often using oxygen or nitrate as electron acceptors. These microbes can fix carbon without the direct use of light-forming localized communities that can persist in darkness at great depth. Although the global contribution of such chemosynthetic production is small compared with that of photosynthesis in the euphotic zone, it represents an important alternative pathway for energy flow in specific deep environments. The interplay between primary production, recycling, and export shapes the distribution of energy and nutrients both vertically and horizontally. Along upwelling margins, sustained nutrient input allows continuous or seasonally recurrent high primary production, supporting dense communities of small grazers and larger consumers, and driving a strong downward flux of organic matter. Over oligotrophic central basins, lower nutrient supply limits, phytoplankton biomass, and energy flow is concentrated in the microbial loop, with relatively few particles reaching the deep sea. In epicontinental seas and restricted basins, the balance between riverine nutrient input, internal recycling, and exchange with the open ocean governs. Whether these systems behave more like productive coastal zones or more like stratified nutrient-limited interiors. Seasonal and longer-term variability overlays these spatial patterns. Changes in wind strength and direction can modulate upwelling intensity, altering nutrient availability and primary production over timescales of years to centuries. Shifts in climate and sea level over millions of years can change the positions of productive zones by rearranging coastline shelves and wind belts. Volcanic episodes that inject ash and dust into the atmosphere can temporarily modify the supply of iron and other trace metals to the surface ocean, potentially stimulating or suppressing primary production in some regions. Over still longer intervals, the evolving balance between weathering on land, hydrothermal activity at ridges, and burial of organic matter affects nutrient inventories and the overall capacity of the ocean to support photosynthetic life. The oxygen cycle is tightly coupled to these patterns of energy flow. Each unit of organic carbon produced by photosynthesis is associated with the generation of oxygen, and each unit respired consumes oxygen. If a significant fraction of the produced organic carbon is buried in sediments without being oxidized, a net source of oxygen to the atmosphere and ocean interior is effectively created. In the early Cambrian interval, many studies suggest that organic carbon burial rates increase relative to earlier periods, contributing to the gradual rise of atmospheric and oceanic oxygen over long timescales. At the same time, locally high rates of primary production and export can intensify oxygen consumption at depth, reinforcing the development of oxygen minimum zones and anoxic basins. Thus, primary production and energy flow cannot be considered independently from the evolving redox landscape of the Cambrian oceans. Energy does not move solely in one direction from producers to larger consumers. At every step in the network, some energy is returned as heat through metabolic processes, and some is lost from the system through the permanent burial of organic matter in sediments. The remaining fraction supports the growth, reproduction, and movement of organisms across size scales from microscopic bacteria to larger animals in the water column and on the sea floor. In early Cambrian time, the exact composition of planktonic communities is still being reconstructed from microfossils, geochemical signals, and comparisons with later periods. But the overall structure of energy flow from light-driven primary producers through microbial recyclers and onward to higher trophic levels is already in place. Within this framework, local differences in nutrient supply, water column structure, and redox state produce a diverse set of energy landscapes across the global ocean. Some regions function as efficient engines that convert abundant nutrients and light into high rates of production and export, while others operate as low-throughput systems with slow turnover and limited transfer to depth. Together, these patterns of energy capture, recycling, and output define the broad ecological backdrop of the Cambrian seas at the scale of whole basins and water masses. Against this backdrop, the more detailed interactions between energy pathways, seafloor surfaces, and the organisms that live at or within the sediment will take shape, but here the focus remains on the large-scale movement of energy through the water column that supports and constrains all later ecological structures. Across the shallow sea floors of the early Cambrian world, a thin but influential living skin covers many sediment surfaces. This skin consists of microbial mats, which are layered communities of microorganisms embedded in sticky extracellular material that binds grains together. Photosynthetic cyanobacteria often occupy the uppermost layer in well-lit settings, forming dense filaments or sheets that trap fine particles and use sunlight to fix carbon. Beneath them, other bacteria and microbes carry out processes such as fermentation, sulfate reduction, and the oxidation or reduction of metal-bearing compounds arranged in vertical sequences according to their preferred chemical conditions. In tidal flats, lagoonal environments, and quiet parts of epicontinental seas, these mats can extend over wide areas, stabilizing the sediment, resisting erosion, and creating a distinct interface between the water column above and the buried sediment below. The presence of microbial mats alters the way sediment responds to physical forces. When waves and currents sweep across the sea floor, loose sand and mud grains would normally be easily entrained and carried away. In mat-covered areas, the sticky extracellular polymeric substances produced by microbes act as a glue that holds grains together. This cohesion raises the threshold shear stress necessary to initiate erosion, so that under the same flow conditions, mat-bound surfaces remain intact, while neighboring unvegetated patches may be reworked. As a result, mats can form small microtopographic highs, such as low ridges and mounds, where sediment is preserved while surrounding areas are stripped. Between tidal cycles, exposure to air and sunlight can cause the upper layers of the mats on intertidal flats to dry and stiffen, further increasing resistance to erosion, until the next flooding event softens them again. These cycles of wetting and drying combined with microbial growth gas production and sediment trapping, generate distinctive textures that later appear in the rock record as wrinkle structures, polygonal cracking, and other microbially induced sedimentary features. Within the mats, steep gradients in oxygen sulfide and other chemical species develop over millimeter to centimeter scales. During daylight, oxygen produced by photosynthetic microbes diffuses downward from the mat surface, while reduced compounds produced below diffuse upward. At night, when photosynthesis ceases, oxygen consumption by respiration dominates, and the oxic zone may shrink or disappear, allowing reduced species to extend closer to the surface. These daily fluctuations overlay longer-term patterns driven by tidal inundation storm events and seasonal changes in light and temperature. Because diffusion through the dense matrix is relatively slow, the mats effectively compartmentalize the sediment surface, creating microenvironments where specific metabolic pathways dominate. This microzoning influences how elements such as carbon, sulfur, nitrogen, and iron are cycled and how they are recorded in the minerals that precipitate within or beneath the mats. The underlying sediment receives a continuous rain of particles from the water column and from lateral transport along the seafloor. Fine grains and organic debris become trapped within the mat fabric or settle into small depressions between microbial structures. Over time, the accumulation of this material combined with compaction and early diagenetic cementation can convert soft mat-bound surfaces into firmer layers. In some settings, the mats grow upward as new layers of microbes colonize the top, while older layers become buried and compressed below, generating thin stacked laminae that record successive phases of mat development. In others, episodic high-energy events such as storms deposit thicker blankets of sediment on top of existing mats, smothering them partially or completely. Surviving microbial communities may then recolonize the new surface, leading to interbedded packages of storm-laid sands and muds separated by mat-formed layers. During the late Ediacaran interval preceding the Cambrian, such microbial mat grounds are particularly widespread, forming the dominant stabilizing cover on many shallow marine sediments. In the early Cambrian, they remain important, but increasingly share the seafloor with animal activity that disturbs and penetrates the substrate. Simple animals and other metazoans capable of crawling, resting, or feeding on or within the sediment begin to leave more frequent and diverse traces. On mat-covered surfaces, some of these animals graze on the microbial biomass, scraping or rasping the surface and leaving behind narrow trails, grooves, or small pits. Others move across the mats, compressing or disrupting the fabric and producing trackways with repeated impressions that reflect their body shapes and movement patterns. Where animals begin to burrow into the sediment below the mats, they create tubes and galleries that cut through laminae, introducing new pathways for water, and solutes to move between the overlying water and deeper pore spaces. This activity, broadly termed bioturbation, alters both the physical and chemical structure of the sediment column. Initially, the extent of bioturbation in many early Cambrian settings is modest. Burrows are relatively shallow and simple, often horizontal or gently inclined, confined to the upper few centimeters of sediment, where oxygen is still available and where mats and surface organic matter provide food sources. The density of burrowing structures varies from place to place. Some environments remain dominated by undisturbed or only lightly disturbed mat grounds, while others show patches in which a network of overlapping burrows has thoroughly reworked the original fabric, creating mixed grounds where primary layering is obscured. The distribution of these patterns reflects local oxygen levels, sedimentation rates, substrate consistency, and the presence of animals with suitable body plans and behaviors. Even where bioturbation remains shallow, its effects on sedimentary processes are significant. Burrowing increases the porosity and permeability of the upper sediment layer, allowing oxygen-rich water to penetrate deeper during each tidal cycle or storm-driven mixing event. This enhances aerobic decomposition of organic matter at depth and promotes the oxidation of reduced compounds such as sulfide and ferrous iron. In turn, this can lead to the precipitation of iron oxides and other minerals in burrow linings, producing distinctive halos around trace fossils. Meanwhile, the physical mixing of grains and organic material by burrowers redistributes food resources within the sediment and blurs the sharp, vertical chemical gradients that mat communities establish. Over long periods, repeated cycles of burrowing and refill can homogenize the upper sediment layer, making it more uniform in grain size and composition compared with underlying strata. Where oxygen in bottom waters is limited, the depth and intensity of bioturbation are constrained. In such settings, mats may retain a stronger influence over sediment surfaces, and reduced conditions may persist just below the mat layer. Burrows in these environments tend to be shallower and may be restricted to periods when oxygen levels in bottom water are temporarily elevated. The interplay between oxygen availability, microbial mat stability, and animal activity thus produces a range of seafloor structures from largely undisturbed mat grounds in persistently low oxygen or low animal abundance settings, to intensely reworked mixed grounds where oxygen-rich waters and active benthic communities coincide. On the flanks of shelves and in deeper parts of basins where light does not reach the seafloor, microbial mats still occur, but differ in composition. Without photosynthesis, mats there are dominated by chemotrophic communities that use energy from the oxidation of reduced compounds diffusing upward from deeper sediments or from the water column itself. These mats may develop at interfaces where oxygenated bottom water overlies sulfide-rich pore waters, for example, and can include layers of sulfide-oxidizing bacteria that form pale filaments or films. Such communities play a key role in buffering the exchange of reduced and oxidized species between sediment and water, controlling the fluxes of sulfide ammonium and other compounds into the bottom water. Their physical stabilizing role is similar to that of phototrophic mats in shallow settings, but their distribution is governed more by chemical stratification than by light. In addition to continuous mats, the early Cambrian seafloor hosts patches where microbial colonization is incomplete or frequently disrupted, high-energy zones subject to persistent wave or current scouring may never allow mats to develop, fully maintaining bare mobile sand sheets, where animals, if present, must cope with unstable substrates. At the other end of the spectrum, very low energy, fine-grained settings in interior basins may support thick laminated microbial deposits, especially where oxygen in bottom waters is scarce and grazing by animals is limited. Here, the vertical stacking of mat layers and the accumulation of organic-rich muds can form distinct sedimentary facies that contrast with the more mixed and burrowed deposits on better ventilated shelves. Over time, the balance between mat stabilization and animal disturbance shifts in many regions. As animal diversity and abundance increase in some environments, the intensity and depth of bioturbation rise, and mat grounds become less continuous. In others, especially where environmental stress remains high due to low oxygen, extreme salinity, or frequent physical disturbance, mats continue to dominate. The resulting mosaic of seafloor states exerts strong control over how sediments are deposited, how chemicals are exchanged between water and sediment, and how traces of life are preserved. In the context of the early Cambrian interval, these interactions between microbial mats, sediments, and early bioturbating animals define the character of the sediment-water interface across vast areas of the continental shelves and shallow basins. The mats act as both stabilizers and filters, shaping small-scale topography and chemical gradients, while animal activity introduces new pathways of mixing and transport. Together, they produce a dynamic but structured environment at the sea floor that responds sensitively to changes in oxygen levels, sediment supply, and bottom water energy, and that will provide the substrate on which later, more complex seafloor communities develop. At the transition from the late Ediacaran interval into the early Cambrian, the seafloor communities that occupy shelves and epicontinental seas begin to change in their basic makeup and in the kinds of bodies that move, rest, and feed on and within the sediment. During much of the Ediacaran interval, many shallow marine surfaces are dominated by the interaction between microbial mats and a set of soft-bodied organisms, with forms that differ markedly from most later animals. These Ediacaran organisms often have simple flattened or frond-like bodies arranged as discs, ribbed ovals, branching quilts, or gently radiating structures that lie on or just above the mat-covered substrate. Their tissues are usually preserved as impressions in fine-grained sediment, and many lack clear evidence for internal cavities, differentiated organs, or mineralized skeletons. For some of these forms, their exact biological affinities remain uncertain. Some may be early animals, others may belong to stem groups related to modern animals, algae, or entirely extinct lineages. What they share in many cases is a reliance on soft external surfaces that exchange solutes directly with the surrounding water and a limited degree of internal differentiation visible in the fossil record. In such bodies, gases and nutrients likely move mainly by diffusion across thin tissues rather than through dedicated circulatory systems, and any internal support is provided by the mechanical properties of the tissues themselves, sometimes combined with fluid-filled spaces that maintain shape. As the Cambrian interval begins, the fossil record shows a shift toward communities that include more clearly animal-like forms with distinct internal spaces, specialized tissues, and in many lineages, mineralized hard parts. This shift does not occur in a single step, and there is some overlap in time between late Ediacaran-style communities and the earliest Cambrian animals. However, by the time extensive early Cambrian sedimentary successions accumulate on many shelves, the dominant macroscopic organisms preserved in them display body architectures that are recognizably similar in basic design to those of later marine animals. Among the earliest indications of this change are assemblages of small shelly fossils. These are tiny pieces of mineralized tissue, often only a few millimeters in size, preserved as isolated plates, spines, tubes, and other simple shapes made of calcium phosphate, calcium carbonate, or silica. Many of these elements probably formed parts of larger bodies, such as protective coverings, skeletal supports, or anchoring structures, although in many cases the complete organisms are not yet known with certainty. Their appearance signals that some lineages have begun to deposit minerals within or on their tissues, producing hard parts that can support, protect, or stabilize the body against gravity and mechanical disturbance. At the same time, trace fossils that record the movement and behavior of soft-bodied animals become more abundant and diverse in early Cambrian sediments. Burrows change from simple, shallow surface trails to more complex, three-dimensional networks that extend deeper into the sediment with branching patterns, spirals, and vertical shafts. Such traces indicate that animals with elongated bodies capable of active locomotion within the substrate are present and that they possess muscular and nervous systems that allow coordinated movement through narrow spaces. The presence of repeated scratch marks, systematic turning patterns, and structures interpreted as resting traces suggests that these animals have defined body axes, sensory structures that detect environmental cues near the sediment-water interface, and the ability to vary their behavior in response to those cues. Body fossils of early Cambrian animals supplement this picture of increasing internal organization and functional specialization. Early representatives of several major animal groups appear, including forms related to arthropods, echinoderms, brachiopods, priapulid worms, and other bilaterian animals. In many of these groups, the body shows a clear front-to-back axis and a top-to-bottom distinction, as well as segments or repeated units along the length. Bilateral symmetry, meaning that the left and right sides of the body mirror each other, is common among these animals. This symmetry is often associated with a head or anterior region, where sensory structures and feeding openings are concentrated, and a posterior region concerned more with locomotion and waste elimination. The development of an internal gut that runs from a mouth to an anus allows food to move in one direction through the body, with specialized regions for ingestion, digestion, absorption, and egestion. Such a through gut separates the processes of feeding and waste removal, in space-reducing interference between them and potentially allowing more continuous processing of food. Surrounding the gut and other internal organs, many early Cambrian animals possess a fluid-filled internal cavity, sometimes called a body cavity or column. This space acts as a hydrostatic skeleton in which fluid pressure provides support for the body wall and internal structures. Muscles attached to the body wall can act against this fluid-filled space to produce movements such as crawling, burrowing, or swimming. In some lineages, the body cavity also hosts circulating fluids that distribute nutrients, gases, and waste products between tissues, forming the basis for more organized circulatory systems. Combined with the development of more efficient respiratory surfaces, such as gills or highly folded body walls, such internal spaces improve the capacity of the animal to sustain higher levels of activity than soft, thin, mat-bound forms that rely purely on diffusion. Externally, early Cambrian animals display a range of coverings and skeletal arrangements that support and shape their bodies. Some worms and vermiform animals retain entirely soft, flexible skins that allow them to squeeze through sediment pores and narrow burrows. Others develop arrays of spicules, plates, or sclerites embedded in the skin, giving the body a tougher, more resistant outer layer. Early echinoderm-like organisms, for example, possess calcite plates arranged beneath the skin in patterns that define their basic body geometry and provide a rigid or semi-rigid framework. Brachiopods grow two mineralized valves that enclose a soft body, attached to the seafloor either directly or by a stalk-like structure. Arthropod relatives begin to show segmented exoskeletons with jointed appendages, in which rigid plates of cuticle alternate with flexible joints that permit precise controlled motion. These structural innovations allow bodies to maintain shape under mechanical loads, resist deformation by currents and waves, and provide attachment sites for more powerful muscles. The interaction between body architecture and the seafloor environment is evident in how these animals occupy space relative to the sediment. Some remain as surface dwellers that crawl, rest, or filter feed on top of the substrate using broad ventral surfaces, multiple legs, or anchoring points to maintain position. Others adopt an infaunal lifestyle constructing burrows or tubes in which they spend much of their time. Tube-dwelling animals may secrete or assemble walls of mineral or organic material that hold open a stable conduit connecting the seafloor to deeper sediment layers. Within these tubes, the body can be elongated and adapted for pumping water, extending feeding structures into the overlying water or withdrawing rapidly when disturbed. Burrowing animals that move freely through the sediment often have streamlined, tapered bodies with reduced appendages and muscular walls, suited to peristaltic movement. In both cases, the shift from living largely on top of stable microbial mats to living within mixed and reworked sediments reflects both the physical state of the seafloor and the capabilities of the animal bodies themselves. Sensory and nervous systems in early Cambrian animals are more difficult to reconstruct directly because soft tissues are rarely preserved in detail. However, body plans and trace fossils provide indirect evidence for increased sensory and behavioral complexity compared with many earlier ediacaran forms. Bilaterally, symmetric animals with defined heads likely concentrate sensory cells at the anterior end, where they encounter environmental cues first as the animal moves forward. Simple eye spots capable of detecting light and dark, ciliated surfaces, sensitive to water movement and chemical sensors that respond to dissolved substances in the water or sediment, would all help guide behavior. Paired nerve cords running along the body with clusters of nerve cells at the head and in each segment provide the wiring needed to coordinate muscular actions across the body. Such arrangements support directed locomotion pattern-based responses to obstacles or gradients and more flexible foraging strategies than those available to immobile or weakly motile ediacaran organisms. Early echinoderm-like and brachiopod animals show different approaches to body support and sensing. Some echinoderm-related forms in the early Cambrian are attached to the seafloor by stalks and present feeding structures into the water column. Their calcitic skeletons support a system of fluid-filled canals and tube-like extensions that aid in movement and feeding. In later representatives and simpler precursors may already be present in Cambrian forms. Brachiopods open their shells to allow water to pass over internal filtering structures that capture suspended particles. Although their bodies do not display bilateral symmetry in the same way as many mobile animals, they maintain clear internal organization with separated regions for feeding support and attachment. In both groups, Mineralized skeletons provide stable platforms for muscle attachment and protect soft tissues from mechanical damage and, to some degree, from environmental fluctuations. Reproductive strategies in early Cambrian animals are inferred mainly from comparison with later relatives. Many marine animals release eggs and sperm into the water column, where external fertilization produces small swimming larvae that join the plankton. These larvae can disperse over distances carried by currents before settling onto suitable substrates and transforming into bottom-dwelling juveniles. If similar strategies are already in place in the early Cambrian interval, they would allow animal lineages to spread across different parts of connected basins, colonizing new shelf surfaces, microbial mat patches, and mixed sediments as they become available. The capacity for dispersal by microscopic stages would link distant populations and contribute to the spread of new body forms and functional types across the seafloor. Not all Ediacaran-style organisms vanish immediately with the onset of Cambrian time, and not all early Cambrian communities are dominated by new animal body plans. There is temporal and spatial overlap, and in some settings, vestiges of mat-ground-associated assemblages persist. However, as the Cambrian interval progresses, fossil assemblages on many continental shelves record a clear trend toward communities in which animals with internal cavities through guts, differentiated muscles, and in many cases mineralized skeletons become increasingly important. Soft-bodied forms without such features become rarer or retreat to specific niches that remain favorable for their way of life. The shift in the dominant types of bodies present on the seafloor thus reflects both the persistence of older strategies and the addition of new anatomical and functional possibilities. Within the broader environmental context of changing ocean chemistry, evolving oxygen distributions, and dynamic sediment surfaces, these early Cambrian animal bodies represent a move toward more internally complex and functionally diverse organisms that interact with the seafloor and water column in ways that differ from the predominantly surface-bound diffusion-limited forms of the preceding Ediacaran world. In the early Cambrian marine world, the new animal bodies that appear on shelves, slopes, and basin floors are not only defined by their internal spaces and tissues, but also by how they move through water and sediment, and by how they sense and respond to their surroundings. Many of these animals share a common feature in the form of bilateral symmetry, in which the body can be divided into left and right halves that mirror each other along a central plane. This symmetry is closely linked to directional movement because it allows the development of a clear front end and back end along the main axis of motion. At the front, sensory structures and feeding openings can be clustered where the environment is first encountered, while muscles and appendages along the sides and rear generate propulsion. In such bilaterian animals, the arrangement of muscles, internal organs, and nerve cords reflects this organization with repeated units or segments along the length of the body that can operate in coordinated patterns to produce efficient crawling, burrowing, or swimming. On the seafloor, elongated worm-like animals illustrate how bilateral symmetry supports movement through soft sediment. Their bodies consist of a series of fluid-filled segments surrounded by a muscular body wall. Circular and longitudinal muscle layers run around and along the body respectively and act against the internal fluid which behaves as a hydrostatic skeleton. By contracting circular muscles in one segment While relaxing longitudinal muscles, the animal can narrow and extend that part of the body into a burrow or between sediment grains. By then contracting longitudinal muscles and relaxing circular ones, it can thicken and pull the rest of the body forward. By repeating this cycle from front to back, the animal produces a wave of deformation that passes along its length, driving the body forward into and through the substrate. Small stiff bristles or spines along the sides may provide frictional anchoring against the sediment during each step of this cycle, preventing backward slip. The result is a steady, controlled progression through the seafloor that leaves behind tubes and tunnels preserved as trace fossils. On firmer substrates or mat-covered surfaces, similar waves of contraction allow crawling across the seafloor with muscular forces directed against the friction between the ventral surface and the sediment. In these cases, movement can be adjusted by biasing the strength or timing of contractions on one side of the body, producing turns or curved paths. Arthropod-like animals and related forms demonstrate another approach to locomotion based on segmented bodies and jointed appendages. In these organisms, a stiff dorsal exoskeleton composed of articulated plates protects the upper surface and provides rigid attachment sites for muscles, while the ventral side carries rows of limbs or lobopod-like extensions. Each limb is divided into segments, connected by flexible joints with antagonistic muscle pairs controlling flexion and extension. To move across the seafloor, these animals coordinate the movements of multiple limbs in repeating patterns, lifting some limbs, swinging them forward, and placing them down while others push backward against the substrate. This produces a metachronal wave of limb motion that travels along the body and propels it steadily forward. Bilateral symmetry ensures that left and right limbs can be synchronized in ways that maintain balance and direction, while the presence of distinct anterior and posterior ends allows the concentration of sensory structures at the front. Some arthropod-like forms in the early Cambrian interval also possess lateral flaps or swimming appendages along their sides. By beating these in coordinated strokes, they can rise slightly above the seafloor or swim within the near-bottom water, improving access to food suspended in the water or allowing faster displacement across the substrate. In the water column, bilaterally symmetric animals use similar principles of repeated coordinated muscular contraction to generate undulatory swimming. Elongate bodies with flexible trunks can produce traveling waves along their length, pushing against the surrounding water and generating thrust. The amplitude and frequency of these waves determine the speed and efficiency of movement. Slight asymmetries in the waveform or in the timing of muscle activation on each side produce turns or allow the animal to maintain a straight course in the presence of currents. In some early Cambrian animals, external fins or fin-like lobes widened certain parts of the body, increasing the area that interacts with the water and enhancing propulsion and maneuverability. These forms can move through 3 dimensions more freely than strictly bottom-bound animals, exploiting gradients in food concentration or oxygen availability within the lower water column. Simple nervous systems underlie and coordinate these varied modes of movement. At their core, bilaterian animals possess longitudinal nerve cords that run along the length of the body, often with paired cords on the ventral side in many groups. Along these cords, clusters of nerve cells known as ganglia serve as local processing centers for each segment or region. From each ganglion, nerves extend outward to muscles and sensory structures carrying signals that initiate contraction or relay information about the environment. At the anterior end, an enlarged concentration of nerve tissue forms a primitive brain or cerebral ganglion, which integrates sensory input from the head region and issues commands that coordinate movement and behavior. This arrangement allows both segmental autonomy, in which local reflexes handle simple tasks, such as rhythmic stepping, and central coordination, which adjusts patterns in response to broader goals, such as migrating toward a food source or away from a disturbance. Sensory systems in early Cambrian animals range from simple diffuse networks of sensory cells spread across the body surface to more concentrated organs specialized for particular cues. Mechanoreceptors, which respond to deformation or vibration, allow animals to detect water movement contact with obstacles or the passage of other organisms. These may take the form of ciliated cells, hair-like structures, or stretch-sensitive endings embedded in the skin or associated with appendages. Chemoreceptors that respond to dissolved substances in the water provide information about the presence of food, conspecifics, or predators through chemical gradients. They can be located on tentacles, palps, antennae, or other protrusions that sweep through the water or probe within sediment. Light-sensitive cells form the basis of visual systems. At the simplest level, they occur as patches of pigment-backed cells that respond to changes in light intensity and direction, enabling animals to distinguish light from dark and to orient relative to the light field. In more elaborate early Cambrian forms, these light-sensitive units are organized into clusters with curved arrangements and screening structures that allow coarse imaging, such as distinguishing the outline or motion of other organisms against the background. The combination of bilateral symmetry and frontally concentrated sensory organs supports an oriented mode of life in which the animal moves predominantly head-first into new environments. As it does, so sensory information from the head region reaches the anterior ganglia quickly, and the resulting motor commands are transmitted rearward along the nerve cords to muscles in trunk segments and appendages. Reflex arcs at the segment level can generate rhythmic patterns such as walking or swimming. Once initiated, while descending signals from the anterior centers can start-stop or modify these patterns. In this way, simple nervous systems can produce relatively complex locomotor behaviors without the need for highly elaborate central processing. Behavioral evidence for such integrated systems appears in early Cambrian trace fossils. Some horizontal burrows display sinuous paths that follow consistent widths and turning radii, suggesting stable patterns of movement generated by coordinated body or limb actions. Repeating series of scratch marks arranged in staggered rows along a trackway imply the alternating use of multiple appendages. Sharp turns, loops, or spirals in burrow networks indicate the ability to change direction, perhaps in response to encountering a patch of food, rich sediment, or an obstacle. Resting traces with outlines that match the ventral surfaces of known body fossils show how animals settled onto the substrate in stable positions, aligning their bodies relative to currents or slopes, which would require sensory assessment of external conditions. In addition to locomotion, simple nervous systems control other movements essential for survival, such as feeding and ventilation. Muscular pumps in the pharynx or body wall draw water through feeding structures or over respiratory surfaces, while valves and sphincters regulate flow. In tube-dwelling animals, coordinated contraction of body wall muscles adjusts position within the tube, extending feeding appendages when conditions are favorable and retracting them when disturbed. These actions often follow stereotyped sequences that can be initiated by specific stimuli, such as a sudden change in light intensity or mechanical contact, and rely on nervous circuits that link sensory input directly to motor output. Integration between nervous, muscular, and supportive systems must operate within the constraints imposed by the surrounding environment. On the seafloor, animals moving over or within microbial mats encounter surfaces whose mechanical properties vary from soft, cohesive films to patchy, eroded sediments. Nervous systems capable of interpreting feedback from mechanoreceptors in the skin and limbs help adjust the strength and timing of muscle contractions to maintain traction and avoid injury. Within the water column, animals swimming through layers with different shear or turbulence must adjust fin beats or body undulations to maintain position or course. Sensory structures that detect flow direction and speed provide the necessary information for such adjustments, while central pattern generators in the nervous system adjust movement rhythms accordingly. The energy demands of these movements are sustained by the internal organization of the body. Through guts, allow continuous processing of ingested food and absorption of nutrients, supporting sustained muscle activity. Internal fluids distribute dissolved oxygen obtained at respiratory surfaces to working tissues and carry away carbon dioxide and other waste products. Simple nervous systems require relatively little energy compared with much larger brains in later animals, yet they provide enough coordination to exploit the mechanical advantages of bilaterally symmetric bodies. In the context of early Cambrian environments, this combination of body symmetry, muscular arrangement, and nervous control allows animals to expand their use of space from static occupation of the seafloor surface to active exploration of sediment layers and near-bottom waters. Different lineages apply these principles in distinct ways. Some emphasize elongate, flexible bodies suited to burrowing with longitudinal nerve cords and distributed ganglia controlling peristaltic waves. Others develop more rigid exoskeletons with jointed limbs where segmentally arranged ganglia coordinate limb movement along each side. Still others retain more radial or irregular external shapes but incorporate bilateral internal structures for feeding and digestion. In each case, the basic link between a defined body axis coordinated movement and a simple but organized nervous system shapes how these organisms interact with physical and chemical gradients in their environment. Within the broader early Cambrian seascape, these developments in symmetry movement and neural control form a crucial part of the shift from mostly passive surface-associated life forms to more actively mobile animals. This shift changes not only how individual organisms obtain food, avoid unfavorable conditions, and occupy habitats, but also how they modify sediments and influence the distribution of energy and matter at the seafloor. At this stage, the emphasis lies on the internal functional relationships that make directed movement and environmental sensing possible within the constraints of early Cambrian bodies and their surrounding waters and sediments. In the early Cambrian seas, animals that move across, within, and above the seafloor must obtain energy and matter from organic resources produced by primary producers and by other organisms. Their feeding modes diversify, and these strategies together build layered structures of who consumes what, when, and where. On and just beneath the sediment surface, deposit feeders take advantage of organic material mixed with mineral grains. These animals, often with elongated bodies, suited to burrowing or creeping, ingest sediment in bulk and process it internally. As sediment passes through their guts, digestive tissues extract organic particles, bacteria, and adsorbed compounds, leaving behind fecal material poorer in readily usable carbon. This mode of feeding changes the physical and chemical properties of the sediment. Grain size distributions can be modified as fine particles are selectively ingested or repackaged, and vertical gradients in organic matter are flattened as surface material is moved downward and deeper material is brought upward. In lightly bioturbated early Cambrian substrates, such deposit feeding produces tubes and backfilled burrows that show where animals have traversed the sediment in search of food. Over time, repeated processing by many individuals can transform sharply layered mat-bound sediments into more homogenized mixed grounds, in which organic matter and grains are more evenly distributed. Suspension feeders occupy a different niche. These animals extract food from the water column, capturing suspended particles such as phytoplankton cells, small organic fragments, and tiny heterotrophs. Early brachiopods, some arthropod-like forms and stem representatives of other groups, employ arrays of tentacles, lopophore-like structures, or setose limbs to filter the passing water. By directing flows across these structures using cilia or rhythmic body movements, they strain food items from the water and convey them towards the mouth. Many suspension feeders live fixed to the substrate and arrange themselves so that feeding structures are elevated into currents above the thin boundary layer close to the seafloor. In this position, they can use the flow field around mounds, burrows, or ripple crests, taking advantage of zones where currents accelerate and deliver a regular supply of suspended material. Other suspension feeders are mobile, using swimming appendages or crawling limbs to maintain positions in favorable microhabitats, where food delivery is high. Grazing on microbial mats and biofilms provides another important feeding mode. Where mats still cover sediment surfaces, small animals scrape or rasp across the microbial carpet, removing cells and extracellular material and leaving behind subdued, smoothed, or patchy mat textures. These grazers may possess hard mouthparts or teeth like structures that abrade the mat surface, and some may carry mineralized elements that stiffen feeding apparatuses. Their activity reduces the continuity of mat cover, opens patches of bare sediment, and alters the balance between sediment stabilization and erosion. In regions where grazing becomes intense, mats fragment into smaller patches or are restricted to refuges in low-energy zones, while the intervening sediment is reshaped by burrowing and physical reworking. Grazing thus forms a bridge between seafloor stabilization by microbes and sediment disturbance by animals. Active capture of larger prey items emerges as a complementary strategy. Some early Cambrian animals are capable of locating, grasping, and consuming other metazoans or sizable organisms, rather than relying solely on suspended particles or diffuse organic matter. These predators and larger scavengers often show adaptations such as grasping appendages, spines, or specialized mouthparts that can seize and process relatively large pieces of tissue. The internal organization of their bodies, including through guts and supportive body cavities, allows them to handle discrete meals and derive energy from concentrated sources. In the sediment, Elongate predators may probe burrows and pores, following chemical or mechanical cues to find buried prey. On the seafloor surface, more heavily sclerotized forms may pursue or ambush other animals that move within the near-bottom boundary layer. Within the lower water column, nectonic or nectobenthic animals can intercept smaller swimmers or suspended forms. Although direct fossil evidence for predation events is limited, drill holes, repaired shell damage, and gut contents preserved in some exceptional deposits indicate that by this time, consumption of animal tissue has become a regular pathway of energy transfer. These feeding modes combine to create a trophic structure that links primary producers, microbial decomposers, and animals in a network of energy and matter flow. At the base, photosynthetic microorganisms in the water column and on illuminated mats fix inorganic carbon into organic forms. Heterotrophic microbes recycle part of this production, breaking down complex molecules and regenerating nutrients. Deposit feeders tap into the pool of organic matter mixed with sediment, effectively mining production that has settled to the seafloor. Suspension feeders connect the suspended particle field of the lower water column to the benthos, channeling material from moving water into stationary or slow-moving consumers. Grazers couple microbial primary production at the sediment surface to the animal community, while predators and larger scavengers link multiple trophic levels. Spatial structure adds further complexity. On gentle shelves, zones near river mouths may support high loads of suspended particles and organic matter favoring suspension feeders that tolerate turbidity and deposit feeders that exploit organic-rich muds. On clearer outer shelves and platform tops, where light penetrates more deeply and water movement is strong but not overly turbid, carbonate-producing communities and filter feeders intercept the flux of plankton and organic fragments transported across the seafloor. In interior basins with restricted circulation, high microbial productivity in surface waters, and slow bottom water renewal can generate organic-rich sediments that support assemblages of deposit feeders and opportunistic suspension feeders, at least where oxygen at the seabed remains sufficient. In each case, the relative importance of different feeding modes shifts according to the balance between sedimentation, nutrient supply, oxygen, and physical energy. Time adds another dimension. Variations in primary production modulate the amount of organic material delivered to the seafloor and suspended in the water column. Periods of high production may see enhanced growth among suspension feeders and deposit feeders, followed by increased activity of predators. During leaner intervals, more energy must be extracted from stored organic matter in sediments. Even in its early stages, this combination of deposit feeding, suspension feeding, grazing, and active capture establishes a multi-layered trophic system that is more complex than the mostly surface-bound communities of many ediacaran settings, and it does so under continuing constraints imposed by ocean chemistry, nutrient cycles, and oxygen distributions. As the early Cambrian interval progresses, the interactions among animals on the seafloor and in the water column increasingly include direct predation in which one organism kills and consumes another. This mode of feeding is not entirely new in Earth history, but the combination of more mobile bodies, more effective sensory systems, and more varied feeding structures makes it a more prominent feature of marine ecosystems than in many earlier ediacaran settings. Predator and prey do not operate in isolation. Their encounters generate ecological feedbacks that alter population sizes, behavior, and morphology across communities and influence how energy and materials move through the environment. On and within the sediment, elongated burrowing animals and surface-crawling forms meet one another in close quarters. Some of these animals specialize in tracking and capturing soft-bodied prey hidden in the upper sediment layers. Chemical gradients leaking from burrows, subtle deformations of the substrate, and small flows of water entering and exiting tubes provide cues that predators can detect with mechanoreceptors and chemoreceptors. Following these cues, a predator can probe into the sediment using its anterior end or specialized appendages, locate the body of a prey organism, and grasp or ingest it. Trace fossils that show disrupted burrow networks or abrupt changes in tunnel diameter may record such events. Over time, repeated encounters of this kind modify how prey use the sediment, favoring deeper retreat, more limited activity periods, or more complex burrow systems that are harder for predators to follow. On the seafloor surface, mobile predators patrol the interface between water and sediment. Arthropod-like animals with jointed limbs and grasping structures can search across microbial mats, mixed sediments, and biogenic structures, encountering grazers, small suspension feeders, and juvenile animals. Sensory input from anterior appendages, simple eyes, and mechanoreceptive hairs informs these predators about the presence and movement of potential prey. When a suitable target is detected, rapid bursts of locomotion allow them to close the distance. Appendages, equipped with spines or claws, seize the prey while mouthparts cut or crush tissue before ingestion. In the water column just above the seafloor, nectobenthic predators intercept swimmers and particles descending from the surface and increase the proportion of biomass that passes through predator guts rather than decaying unconsumed. The presence of such predators exerts selection pressures on potential prey. Soft-bodied organisms that previously could move slowly along the seafloor or maintain exposed positions on microbial mats now face higher risks. Individuals that move more quickly, change direction abruptly, or detect approaching predators have a higher chance of surviving long enough to reproduce. Over many generations, these advantages can lead to bodies with more robust musculature, more efficient locomotory patterns, and improved sensory arrays. Behavioral changes, such as spending more time in burrows or using cryptic resting positions, further alter how communities occupy the available space. The shift from mostly static to more responsive behaviors modifies the physical impact of animals on sediments because frequent burrow construction and movement create more pervasive bioturbation, which affects how oxygen and nutrients are transported into the sediment and how organic matter is buried. Predation pressure also influences the density and distribution of grazers and suspension feeders. Where predators are abundant surface grazers may be kept at lower population densities, allowing microbial mats to persist in some refuges that would otherwise be heavily consumed. In other places, predation on suspension feeders that extend their bodies into the water column can reduce filtration rates, altering the clarity of near-bottom waters and the amount of particulate organic matter that reaches the sediment. These shifts in community composition feed back on food availability for predators, because changes in prey abundance affect predator growth and reproduction. More gradual directional feedbacks are also important. Predators that develop more effective sensory systems, such as improved light detection, gain access to a wider range of prey behaviors. In clearer waters over some Cambrian shelves, the contrast between bodies and background allows simple eyes to detect movement and shapes at useful distances. A predator that can see prey earlier can begin its approach sooner and adjust its path more accurately, increasing capture success. Prey species that are routinely hunted in this way may benefit from behaviors that keep them within shaded or sediment-filled microhabitats, or from body surfaces that disrupt visual outlines. The emergence of more active predation also influences the development and use of protective structures. Some animals thickens their external tissues or reinforce them with cuticle or mineralized elements, making it harder for predators to bite through. Others adopt shapes that reduce the number of vulnerable regions, such as compact forms that present fewer protruding parts or spines that make ingestion difficult. These features come with energetic costs, both in constructing the protective layers and in carrying the extra weight or overcoming increased drag. In environments where predation risk is high, the survival benefits can outweigh these costs, so that populations with more effective defenses become more common. Ecological feedbacks extend beyond individual predator-prey pairs to affect whole seafloor landscapes. Active predators moving across microbial mats and bioturbated sediments do not only consume prey, they also stir the upper sediment layer, resuspend fine particles, and displace small organisms. Their trails may open temporary pathways for oxygen-rich water to penetrate into previously stagnant pore spaces, while their disturbance can fragment mat surfaces and redistribute organic matter. In turn, the altered sediment structure influences where prey can build burrows, how mats regrow, and how chemical gradients are established. Over long periods, this interplay between predation movement and sediment response contributes to the transformation of many Ediacaran-style mat grounds into the more mixed substrates characteristic of Cambrian seafloors. The rise of predation changes the fate of organic matter in the system. Instead of a large fraction of biomass following relatively direct paths from primary producers to decomposers, more passes through predator and scavenger pathways. Prey carcasses that are only partially consumed become localized sources of organic matter for microbial communities and small detritivores. Gut contents of predators preserved in some early Cambrian fossil deposits show recognizable remains of other animals, confirming that such pathways are part of the regular energy flow. Through these mechanisms, predation and the associated ecological feedbacks become central components of early Cambrian marine ecosystems, shaping the behavior and morphology of both predators and prey, reorganizing sedimentary environments, and altering how energy and matter are partitioned between living biomass and buried organic carbon within the broader context of changing ocean chemistry and evolving animal body plans. As early Cambrian ecosystems develop more active predators and more mobile prey, another conspicuous change appears in the fossil record, the wider spread and diversification of skeleton shells and other hard parts. These mineralized structures are not uniform in material or form. Instead, different animal lineages adopt different ways of incorporating inorganic minerals into their bodies, and they do so more than once in separate evolutionary experiments. The materials most commonly used include calcium carbonate in forms such as calcite and aragonite, calcium phosphate, and silica. Each mineral brings its own mechanical properties, solubility characteristics, and energetic costs. The decision in evolutionary terms to invest in a skeleton or shell reflects a balance between protection and support on one side and the demands of building and maintaining mineralized tissue on the other. Early evidence of this trend comes from small shelly fossils that appear in lower Cambrian strata on many continents. These assemblages contain tiny plates, spines, tubes, and cap-shaped elements only a few millimeters long, preserved as isolated fragments in sediment. Some are made of calcium phosphate, others of calcium carbonate or silica. Many likely form parts of larger composite exoskeletons or protective coverings for soft bodies, though the complete animals are not always known. Their scattered distribution in sediment suggests that even before large, fully skeletonized animals become common, many organisms have already begun to experiment with adding hard parts to their external surfaces. These structures may have served as defensive armor against predators, as anchors for muscles, or as supports for feeding appendages extended into the water column. As the Cambrian interval progresses, more fully skeletonized animals appear in the fossil record. Trilobites, with their articulated dorsal exoskeletons, become among the most recognizable inhabitants of Cambrian sea floors. Their bodies are covered by a mineralized cuticle, reinforced with calcite, arranged in a head shield, a segmented thorax, and a tail plate. Beneath this rigid shell, the ventral side carries limbs that remain mostly unmineralized, allowing flexibility and complex movement. The exoskeleton protects the soft tissues from mechanical damage, and predation gives shape to the body and provides surfaces for muscle attachment. It also constrains growth so that trilobites and similar arthropod-like animals must periodically molt, shedding the old exoskeleton and secreting a larger one. This mode of growth leaves abundant molts in the sediment, which contribute to the fossil record. Brachiopods present another mineralization strategy. They secrete two shells or valves that enclose a soft body attached to the seafloor by a stalk or by direct contact. The shells may be made of calcite, aragonite, or combinations of mineral and organic layers, depending on lineage and environmental conditions. Inside the soft body supports a feeding apparatus that filters particles from the water. The mineralized valves protect the internal organs from predators and physical disturbance and create a stable internal space where water flows can be controlled for feeding and gas exchange. The hinge and muscle attachment points must be strong enough to allow repeated opening and closing over the life of the animal. Energetically building such shells requires a continuous supply of dissolved ions and control over the chemistry at the site of mineral deposition to ensure that crystals grow in the correct orientation and size. Echinoderm-related forms add another variant. Their skeletons consist of numerous calcite plates arranged in a three-dimensional mesh under the skin. The plates can articulate or be more firmly fused depending on the group and life habit. Some early echinoderm-like organisms attach to the seafloor by stalks and extend feeding structures into the water, while others lie on or just above the sediment. The skeleton provides a rigid framework that resists compression and bending, allowing the animal to maintain posture in moving water and to support the weight of extended arms or feeding structures. It also acts as a site for storage of certain ions and may participate in buffering internal acid-base balance. However, Calcite is sensitive to changes in seawater chemistry, especially in deeper or more carbon dioxide-rich waters where carbonate saturation is lower. Animals relying on such skeletons are therefore more constrained to environments where conditions allow net precipitation and stability of their skeletal material. Not all skeletons are external. Some early Cambrian animals use mineralization internally, forming spicules or rods embedded within tissues. These elements can stiffen the body without forming a continuous surface armor. For example, small spicule-bearing animals may use networks of mineralized needles to support soft tissue without fully enclosing it, allowing flexibility while still gaining some mechanical advantage. In other lineages, calcium phosphate is deposited in tooth-like structures or feeding elements that experience repeated mechanical stress during feeding. Phosphate minerals can be more resistant to dissolution under certain conditions and can form harder, more abrasion-resistant surfaces than some carbonate structures. The coexistence of different mineral types in the same time interval suggests that ocean chemistry does not dictate a single solution, but it does influence which strategies are more easily realized in particular regions. The energetic cost of biomineralization includes both the production of organic matrix that guides crystal growth and the active transport of ions against gradients. Animals must regulate the chemistry of the fluid in which minerals precipitate, often in microscopic spaces close to cells. This requires enzymes, membrane pumps, and controlled secretion of organic molecules. The payoff comes in the form of improved defense support and sometimes improved locomotion. Rigid exoskeletons allow the development of lever systems in which muscles acting on hard levers produce efficient movement, while shells and plates resist crushing and penetration by predators. In environments where predation is intense, populations with more effective hard parts are more likely to survive and reproduce, reinforcing the spread of biomineralization despite its costs. Hard parts also alter how animals interact with the seafloor physically. Heavier shells and skeletons increase body mass and affect how organisms rest on or sink into the sediment. Some bivalved animals and brachiopods distribute their weight over broad surfaces to avoid sinking, while others partially bury themselves using shells as shallow anchors. Trilobites and similar arthropod-like forms may plow shallow furrows as they move, redistributing sediment and influencing small-scale topography. When skeletonized animals die, their hard parts add coarse particles to the sediment, changing grain size distributions and creating new microhabitats where smaller organisms can shelter or attach. Over time, accumulations of shells and skeletal debris form layers of carbonate-rich sediment that participate in the long-term carbon cycle. The emergence of skeletons and shells also changes how dead bodies are preserved. Soft-bodied organisms without hard parts decay quickly and often leave only faint impressions, whereas mineralized structures can remain intact for longer, resisting physical and chemical breakdown. This differential preservation means that the early Cambrian fossil record is biased toward skeletonized forms, potentially exaggerating their relative abundance compared with soft-bodied animals. However, where exceptional preservation occurs, such as in fine-grained deposits that retain both hard and soft tissues, it becomes clear that skeletonized and non-skeletonized organisms coexist. Within this mixed framework, the presence of hard parts provides insights into the distribution of functional types across environments. Regions with abundant skeletonized benthos may indicate conditions where carbonate saturation and nutrient supply together support both the construction of shells and the activity of predators that select for them. In contrast, settings where soft-bodied forms remain dominant may reflect lower saturation states, lower predation pressure, or other constraints that make biomineralization less advantageous. Over millions of years, the spread of skeletons and shells contributes to the broader evolution of marine ecosystems by enabling new modes of life. Rigid frameworks make possible larger body sizes and more powerful movements, while protective coverings permit riskier foraging strategies in exposed positions. The varied mineral compositions and architectures adopted by different lineages illustrate that biomineralization is not a single event, but a suite of innovations that arise repeatedly in response to local ecological pressures and the prevailing chemical environment of the Cambrian seas. Within the context of changing oxygen levels, nutrient regimes, and predator-prey dynamics, these hard parts become key components in the physical and biological structure of early Cambrian marine communities. In early Cambrian animals, the variety of body shapes seen on the seafloor and in the water column rests on underlying systems that control how bodies are built from fertilized eggs. These systems are based on genetic instructions and on ways in which those instructions are turned on and off in different places and at different times during development. Although the details of these processes are not preserved directly in fossils, comparisons with living animals, and the shared features of their body plans suggest that many of the basic developmental controls already exist by the time diverse Cambrian forms appear. A useful way to think about these controls is as a set of instructions and switches that guide where segments form, where limbs grow, how front and back are distinguished, and how tissues differentiate into skin, muscle, gut, and other structures. In bilaterian animals, which have left-right symmetry and a clear front-to-back axis, the embryo begins as a simple ball or sheet of cells. As it develops, gradients of signaling molecules and the activity of certain key regulatory genes divide this simple structure into regions. Some genes are active mainly at the front, others at the back. Some mark dorsal regions, others ventral regions. These early patterns provide a course map that later steps refine into segments, appendages, and organs. Regulatory genes are genes whose main role is not to build structural proteins, but to control other genes. They act like switches that can turn sets of downstream genes on or off in response to signals. Many of them encode proteins that bind to DNA and influence whether nearby genes are transcribed. In modern animals, families of such regulatory genes, including those that pattern the main body axis and define segment identity, are shared across very distant groups from insects to vertebrates. This shared heritage suggests that a common set of regulatory tools is already present in the ancestors of Cambrian bilaterians and is being used, modified, and combined in different ways to produce the range of body plans recorded in Cambrian fossils. Once the main axes of the body are established, development proceeds through repeated cycles of patterning and growth. In some lineages, segments form one after another from a growth zone at the rear of the embryo. Each new segment arises as a block of tissue in which certain genes are active in stripes or bands. Other regulatory genes then specify differences between segments, for example, distinguishing those that will carry limbs from those that will not, or those that will form mouth parts from those that will form walking legs. In this way, a combination of repeated segmentation and segment-specific identities generates a series of similar, but not identical, body units. Trilobites and other arthropod-related Cambrian animals show external evidence of such segmented organization in their dorsal exoskeletons, with repeated thoracic segments that nonetheless differ in detail between head trunk and tail regions. Limb development also follows rules that reflect underlying genetic and developmental systems. Where limbs or lobes form along the body, local interactions between tissues determine how many limb buds appear, how they branch, and how they differentiate along their own axis from base to tip and from front edge to back edge. Regulatory genes that are active in specific domains within each limb bud guide the formation of joint spines and sensory surfaces. Cambrian arthropod-like fossils with repeated pairs of appendages along the body suggest that such limb patterning systems are already in use, producing arrays of limbs that share basic structure but vary in detail according to their position and function, such as walking, swimming, or feeding. In animals that filter feed or attach to the substrate, such as early brachiopods and echinoderm-related forms, development must generate both a stable attachment or shell region and specialized feeding structures. The shell-secreting tissues of brachiopods form along specific parts of the outer body wall under the control of genes that regulate tissue type and growth pattern. Inside, another set of patterning processes shape the feeding apparatus, arranging ciliated surfaces or arms in configurations that allow efficient particle capture. Early echinoderm-like animals, although not fully radial in the same way as many later forms, already show organized arrays of plates and feeding structures that reflect developmental rules, controlling where calcite plates are added and how arms or extensions branch from the main body. Even in soft-bodied worms and vermiform animals without extensive skeletons, developmental systems must establish the structure of the gut, the arrangement of muscles, and the placement of nerve cords. Formation of a through gut from mouth to anus involves coordinated invagination and fusion of tissues during early development under the guidance of signaling pathways that specify endodermal, mesodermal, and ectodermal layers. Muscles develop from mesodermal cells that differentiate into circular, longitudinal, or oblique fibers according to their position. Nerve cords arise from ectodermal regions, where cells adopt neural fates, later organizing into cords and ganglia. The regularity of these features across many bilaterian lineages suggests that by the Cambrian interval, common developmental pathways for building guts, muscles, and nervous systems are already established and can be deployed in different combinations and proportions. A key feature of these developmental systems is modularity. Modules are groups of genes and developmental interactions that control a particular structure or process, and that can to some extent operate independently. For example, the module that patterns the main body axis can function in a range of contexts, while separate modules handle limb formation or sensory organ development. Evolution can then alter body plans by changing when and where these modules are activated, or by modifying their internal details rather than by inventing entirely new sets of genes for each new form. Small changes in timing, often called heterochrony, can shift when a module acts during development, affecting relative sizes of body regions. Changes in location, sometimes called heterotopy, can shift a structure from one region to another. In the Cambrian context, such alterations could underlie differences in the number of segments, the distribution of limbs, or the extent of skeletal plates seen among related fossil taxa. The presence of similar body plan themes in distantly related Cambrian animals supports the idea that many lineages are drawing on a shared set of developmental tools. Bilateral symmetry, segmented trunks-paired appendages through guts and internal cavities occur in multiple groups that otherwise differ in their external coverings and life habits. At the same time, unique combinations and modifications of these features produce the diversity of forms documented in deposits such as the Burgess Shale and similar assemblages elsewhere. Some animals emphasize a large head region with complex appendages. Others build extended series of nearly identical segments, and others adopt more compact bodies with limited regional differentiation. These variations can be understood as different ways of applying and adjusting underlying developmental modules. Mineralized skeletons and shells described earlier also depend on developmental control. Cells that produce mineral must be specified at the right positions on or within the body and must follow precise patterns of secretion to create plates, spines, or shells with consistent shapes. Regulatory genes link the positional information that defines body axes and segments to the activation of biomineralization pathways in certain regions. For instance, in trilobites, the repeated thoracic segments carry similar exoskeletal structures, implying a developmental link between segment identity and the deployment of mineralizing cells. In brachiopods, shell-secreting tissues form in matched regions on each side of the body, reflecting bilateral symmetry and controlled differentiation of the dorsal and ventral body walls. The fossil record cannot show the genes themselves, but the consistent patterns of skeletal geometry among individuals of a species indicate that tightly regulated developmental programs are in place. Over evolutionary timescales, changes in developmental systems alter the range of possible body plans. Some modifications open new regions of form space, such as additional segments, new appendage types, or expanded head regions with more sensory organs. Others constrain variation, as when a highly integrated skeleton limits the ways in which plates can be rearranged without losing function. In the early Cambrian interval, the emergence of many new body architectures suggests that developmental systems are flexible enough to permit exploration of diverse designs within the general bilaterian framework. At the same time, the recurrence of certain themes across multiple groups points to shared rules that shape what forms are most accessible. Within this view, the variety of Cambrian body plans is not a random collection of shapes, but the outcome of interacting developmental controls that guide how embryos and larvae build adult structures. These controls operate under the influence of environmental conditions, such as oxygen and nutrient availability, and within ecological contexts that include competition, predation, and opportunities for new modes of life. The internal rules of development, together with external conditions, determine which body patterns persist and become common on Cambrian sea floors and in their overlying waters. The changes that take place in ocean sea floors and animal bodies during the early Cambrian interval are known mainly from what remains in the rocks, and this record is incomplete and selective. Sedimentary layers that formed on continental shelves, slopes, and in deeper basins preserve shells. Skeletons trace fossils, and in a few exceptional cases, soft tissues. Each type of evidence reflects a combination of original biological signals and later physical and chemical filters. Understanding what changed on Earth during the Cambrian interval requires attention not only to what is preserved but also to what is lost and to the ways in which preservation varies across regions and environments. In many successions, the most obvious Cambrian fossils are those with mineralized hard parts. Trilobite exoskeletons, brachiopod shells, echinoderm plates, small shelly elements, and other skeletal pieces occur in large numbers within carbonate and siliciclastic rocks. Their stratigraphic ranges and geographic distributions allow the construction of relative timelines that show when particular groups first appear, diversify, and decline. By comparing these patterns across continents, it is possible to identify intervals of rapid increase in recorded diversity and shifts in community composition near the base of the Cambrian interval and in later stages. However, these trends are influenced by the fact that skeletonized animals are more likely to leave recognizable fossils than soft-bodied organisms. As a result, the apparent timing of diversification in the rock record may be shifted relative to the true history of living communities, especially for lineages that acquire mineralized hard parts after they have already existed in soft-bodied forms. Exceptional fossil deposits that preserve soft tissues offer additional perspectives. In such deposits, fine-grained sediments, rapid burial, and specific chemical conditions combine to allow the preservation of muscles, guts, gills, and even delicate sensory structures as films, carbonaceous compressions, or mineral replacements. Assemblages of this kind reveal a broader spectrum of Cambrian life, including many animals with little or no mineralized tissue. They show complex arthropod-like forms with elaborate appendages, worms with internal organs visible, and soft-bodied predators that rarely appear in ordinary shelly assemblages. They also record non-animal organisms such as algae and some microbial structures. These sites indicate that the variety of body plans and ecological roles present in Cambrian oceans extends beyond what shell beds alone suggest. At the same time, such deposits are rare and geographically localized, so they may not capture the full range of environments or communities that existed globally. Trace fossils provide another line of evidence. Burrows, trackways, resting impressions, and feeding traces are preserved where animals interacted with sediment in ways that left durable structures. The appearance of deeper, more complex, and more vertically extended burrows around the Ediacaran to Cambrian transition signals an increase in sediment penetration and mixing by animals, even where body fossils are scarce. Changes in the diversity and complexity of trace fossils through the lower Cambrian interval indicate that behaviors related to locomotion, feeding, and dwelling continued to diversify over millions of years. Because trace fossils do not depend on skeletal mineralization, they help document the expansion of animal activity into new sedimentary environments, including some where chemical conditions may not favor preservation of shells. Geochemical measurements complement these paleontological records. Ratios of stable isotopes of carbon and sulfur in carbonate and organic matter track. Changes in the burial of organic carbon and in the cycling of sulfate and sulfide. Variations in these signals across the Ediacaran to Cambrian boundary and within the Cambrian interval point to shifts in the balance between organic matter production, respiration, and burial, as well as changes in global redox conditions. Trace metal concentrations and iron speciation in sediments provide information about the distribution of oxygenated and anoxic waters as described earlier. Together, these chemical records suggest that the interval leading up to and through the early Cambrian is marked by fluctuations in ocean oxygenation and nutrient availability, with episodes in which oxygenated conditions expand and others in which low oxygen waters are more widespread. These patterns form part of the environmental backdrop against which animal diversification occurs. Despite the wealth of data, several aspects of the Cambrian interval remain uncertain. One unresolved question concerns the exact timing and tempo of diversification. Fossil records from different regions do not always show identical patterns. In some areas, small shelly fossils appear earlier or later than in others, and the first occurrence of particular groups such as trilobites can vary between basins. Part of this variation reflects genuine regional differences in environments and faunas, while part reflects differences in sampling preservation and the completeness of rock successions. Establishing precise timelines requires integrating biostratigraphy, with radiometric age determinations from volcanic ash beds, and not all sections contain suitable material for precise dating. As a result, estimates of how quickly diversity increases and how abrupt certain changes are still carry ranges of uncertainty. Another area of ongoing study is the relative importance of different drivers in promoting the observed changes. Rising oxygen levels post-glacial nutrient inputs, evolving developmental toolkits, and intensifying ecological interactions all likely contribute, but quantifying their individual and combined roles is challenging. Oxygenation appears to improve over long time scales, yet oxygen-rich conditions exist locally before the main phase of recorded diversification. Developmental gene networks that allow bilaterian body plans probably arise before the earliest shelly fossils, as suggested by molecular clock estimates. But the exact timing of these genetic innovations relative to morphological change remains debated. Ecological feedbacks involving predation and bioturbation clearly become more important during the Cambrian interval, but reconstructing their onset and strength in different habitats relies on indirect signatures such as damage on shells, the spread of trace fossils, and the appearance of defensive structures. These lines of evidence are informative but not complete. Preservation filters also complicate interpretations of extinction and turnover. Ediacaran-style soft-bodied assemblages diminish in abundance and diversity in many settings near the base of the Cambrian interval, while shell-bearing animals and new trace fossil types become more prominent. Whether this change reflects a true global extinction of many Ediacaran organisms, a shift in where and how they live, or a change in the conditions that favor their preservation is still under investigation. Possible catastrophic events near the boundary, such as environmental disturbances that could remove particular communities, are difficult to document directly, because physical evidence for such events may be subtle or overprinted by later processes. At the same time, the gradual appearance of bilaterian animals in late Ediacaran rocks suggests that some lineages span the boundary, and that the transition from Ediacaran to Cambrian ecosystems involves both loss and continuity. Spatial variation adds further layers. Some basins record rich assemblages of early Cambrian fossils, while others preserve only sparse remains or have rock gaps that remove key intervals. Differences in sedimentation rate, tectonic history, and later erosion all influence which slices of the Cambrian world are available for study today. As a result, reconstructions of global patterns must combine information from multiple regions, each with its own biases. Comparing faunas from different paleocontinents helps identify broad trends, such as the spread of trilobites and the diversification of brachiopods. But local environmental factors always influence the details. Taken together, the fossil record of the Cambrian interval provides strong evidence that seafloor environments, ocean chemistry, and animal communities undergo substantial changes over tens of millions of years. It shows the spread of deeper bioturbation, the rise of skeletonized animals, the diversification of bilaterian body plans, and the restructuring of food webs to include more active predation and more complex trophic interactions. It also records fluctuating oxygen levels and nutrient regimes that shape where different communities can thrive. At the same time, gaps in preservation, regional differences, and uncertainties in timing leave room for multiple contributing processes and for active research on how these processes combine. The Cambrian fossil record is therefore both a window onto past oceans and a set of filtered signals that must be interpreted with care to understand what changed on Earth during this formative interval in the history of animal life.